בוקר טוב לכולם. Good morning everyone. I'm really excited having you here. אני אדבר גם קצת בעברית וקצת באנגלית, יש לנו אורחים מהארץ ומחול. Thank you everyone for joining us by Zoom. Hopefully you hear us. We are working on the sound that it will work fine. You can write on chat too questions or remarks. My name is Adi Mager and I'm happy that you join us. There were over 200 registered to this conference, which is not something that we thought about. It's an honor to be in a conference talking about circular economy and the built environment. I'm a PhD student here in Dr. Vered Blas' laboratory on the first floor. She will talk about it, the laboratory and her researchers. The program of today will begin with guest lectures and then researchers presenting, and afterwards we'll have a panel talking about the practical world. How can we take the academic world, the researchers, into the regulation and the industry practice? What are the obstacles and what are the opportunities? I would like to first say thank you to Professor Shai Zucker, head of the Porter School of the Environment, coming this morning and say a few words. Thank you, sir.
Hello, and welcome to the Porter School of the Environment and Earth Sciences. I browsed the program of this conference and was impressed by the importance and relevance of the topics and ideas that you will discuss here today. I myself am not an expert in circular economy or related topics. I'm an astrophysicist in my training. And my expertise is the search for exoplanets, planets that orbit stars other than our sun. Of course, the holy grail in my field is finding life on such planets. It is part of the growing interdisciplinary and respectable nowadays field of astrobiology, life in space. Astrobiologists study, among other things, what makes a planet habitable. And we come to realize how complicated is habitability and fragile. You deal with habitability as well, and you study ways of preserving the habitability of Earth while advancing the technological aspects of human life. In principle, while studying the potential of other planets to host life, we may very well encounter technological civilizations, who knows? They might be facing the same challenges that you try to solve, and we may have a lot to learn from them. That's how our fields are related. I wish to you and all of us that if and when we do meet them, thanks to your work, they will have a lot to learn from us. So please, while saving the habitability of Earth and maybe of other planets as well, have a great and fruitful conference here today at the Porter School.
Thank you. Well, I'll tell you a short story about myself. I'm a geographer. I did my first degree and my second degree here in Tel Aviv. So I love Tel Aviv University. And to do my PhD here is quite a challenging one because it's a multidisciplinary PhD. And this is what we're going to say today. We're going to have multidisciplinary researchers and examples and discussions. So feel free to take part in it. Write questions, ask questions. Do mingling, it's important for us to hear you. I know some of you asked about the schedule. We'll explain later on. Now we're just in the greeting section. Now I'm very excited to invite Professor Alexander Goldberg, head of the Department of Environmental Studies in Tel Aviv University. Thank you, sir.
Okay, so thank you for the invitation. And I'm very happy to see all of you here physically. So this is a great event that we're actually able to host you, and you're able to come after 2 years and a half that everything was remote, and we actually see people and you see us, and we're very, very excited about this. So the issue of the topic of the components of circular economy is very close to me. For example, we do a lot of work about industrial ecology and circular economy, but in the marine environment. So my lab here does a lot of work on seaweed cultivation and processing to food, energy, materials, plastic, and so forth. So we do a lot of things, and we also have these topics very heavily introduced in our curriculum. So we have them both in the undergrad program we have jointly with the mechanical engineering and geophysics, and the environmental part in that program deals a lot with the industrial economy and circular economy. And in the graduate programs we have those different courses which Vered leads, and a few others which deal with the systems analysis and how they integrate all together. On the national level, I think that circular economy in Israel now is a very hot topic. So there are multiple spots available now, and which are developing over the country. And I think that our department, if we will be able, together with partners and collaborators, to keep the academic knowledge in this field and support the industry, support the government, support the municipalities, that will be a big deal. So all this field will move forward. So I wish you the great conference and the integration of circular economy in the city, and we are in the biggest city in Israel. Enjoy.
Just yesterday, we had a delegation from Denmark where I talked to them about construction industry and the growth of population in Israel. And they were so surprised that Israel population is 9 million people approximately, and we're going to double it in the next 20, 25, 30 years. They were like, what? So we know the challenges. And this is, again, the opportunity to say thank you. Thank you, Vered, Dr. Vered Blas, the head of the Innovation in Industrial Ecology Lab, the Department of Environment Studies here in Tel Aviv University, for approving my idea to collaborate with the Technion, with Professor Sabrina Sbarti, and Shani Barak, together with the Technion and Tel Aviv University, to arrange this conference. I couldn't have done it without you, and with you, it's a power, not just a woman power, but academic power. So thank you all. Vered, the stage is yours.
Thank you, Adi, and welcome everybody, and good morning. I'm really delighted to be here today. For me, it's like closing the loop, closing the circle, you know, coming back to Israel 13 years ago when I spoke on the concept of industrial ecology, circular economy, resource efficiency. Everyone looked at me as like the crazy lady. What the hell is the connection to the environment? And I'm really delighted to see the progress in quite short time, how the conversation around it is much more flourishing and existing in government offices, in academia, in industry. I think we are in a tipping point when we move from theory to practice, where all of us needs to really get an end together and make it progress. I'm also very delighted for this collaboration with Shani and Sabrina. It's the first time we collaborate on such an event, but it's really amazing to see, you know, us young people in academia bringing together really different disciplines, all talking in the same concept from different point of views. And of course, thank you, a big thank you to Adi, that without her, this conference would not happen, and also other lab members that help us, like Tal and other people. So enjoy the day. We will start now with the research session. Later on, we will have the industry and government session, and then we will have our guest speaker from Canada, that by the time we get there, she will be awake and ready to talk with us via Zoom. So enjoy the day.
So we're going to have our first session today, the research session. The role of the Israeli Academy in research and application of a circular economy in planning and construction perspectives on the conference topic and relevant research. This is an opportunity to hear the three different professors and architects about their expertise and research. So first we'll start with Professor Sabrina Sbarti, head of PSAIL, Prospective and Early Stage LCA Lab, Faculty, Civil and Environmental Engineering in the Technion. Thank you, Sabrina, for joining.
Well, thanks very much. And I'm very pleased and delighted to be here to visit Tel Aviv University. Actually, it's been more than 4 years since I've been here. And I gave a seminar here in this very lecture hall, not at that time. So I want to speak for a little bit about the work that we're doing in my lab, prospective and early stage LCA lab at the Technion. We are working mainly on evaluating early stage technologies in multiple areas, including renewable energy, biomass and bioenergy. I've done a lot of work in this area, and so my students are continuing this work. Solar PV, adding solar PV technology into the built environment, building and infrastructure materials, and I'll talk about a little bit about one of our studies in the short introduction today, and overall analysis and processes and tools to reduce construction waste in Israel. In fact, my student Musab Maraka is going to be presenting this a little bit later this morning. But with prospective life cycle assessment, we look to understand the environmental impacts of early stage technology before we invest and scale up. And so this takes place in a variety of areas noted above, but I want to talk about the work we've done on mechanical recycling of post-consumer plastic waste. So we know that plastic has become a major global problem, especially in our oceans, in the environment. This slide comes from the Ellen MacArthur Foundation, which has projected that by 2050, there will be more plastic in the ocean than fish, which means we won't have much of an ocean. And so in addition to that, another problem with plastic is its extreme energy and greenhouse gas intensity. This number here from work of Song-Won Su estimates that annually close to 2 million metric tons of greenhouse gases are released for the whole life cycle of plastics, all plastics produced. So we know that they're energy intensive. And if you see this blue area of the slide, that refers to only the production phase. So producing plastics is energy intensive. So with this, I want to say there are two major problems that we see with plastics. At least there are more, but the ones that I want to address include that the material does not decompose, and it is problematic when it enters the environment. We have a lot of complex products that have short lifetimes, and they're not managed well around the planet. So in addition to that, mechanical properties of these materials deteriorate, making it even more difficult to recover them and put them into new products. Our manufacturing economy is designed to have good, clean resin for new products. And then finally, that plastics are greenhouse gas intensive to produce. We can overcome this through making biorenewable resources for plastics, but that doesn't solve the problem at end of life unless we go toward biodegradable plastics. In the end, biodegradable plastics don't produce any value except more CO2 in the atmosphere, albeit if from biological resources, it happens in a closed loop. So I want to talk a little bit about a study that we did years ago with my students that looked at possible uses of beneficial uses of recycled high-density polyethylene in infrastructure materials. So the idea was that we can take post-consumer waste like plastic milk jugs, which are produced en masse in the US, and it's a relatively clean and transparent resin, no colors added. We can mechanically recycle these and extrude them into new pipe. Lots and lots of plastic pipe used in infrastructure. So what we did in this study was we looked at 4 different alternatives. Our pristine resin, made from virgin resources, a blend of recycled and virgin material, an upgraded material with nanoclay to improve the mechanical properties. And then we also looked at a bio-derived, so you can convert lignocellulose, biomass from agricultural residues, into resin to make a renewable feedstock. So we looked at these 4 alternatives, and the results were disappointing, I should say. When we look down here at these 4 alternatives, so this is our pristine resin, 3 different scenarios, our recycled blend, and our nanoclay, our advanced material, and this is our biomaterial. This is 1 metric, greenhouse gas emissions. If you compare using recycled resin and using this advanced material with nanoclay, your greenhouse gas emissions increase over the lifetime, a 100-year service life for the product. And the reason for that is that the mechanical properties make this material not as durable, and therefore you need more replacement time, or you need thicker walls of pipe. So you can never get around this limitation. When you look at it from a life cycle cost perspective, this is a discounted cash flow. The costs of, because of that replacement of the nanoclay are actually roughly on par within a standard error of the pristine material. So although you may have a somewhat more cost-effective material over a 100-year lifetime, you increase greenhouse gas emissions. However, the trade-off is that you would be somewhat addressing the solid waste problem and keeping it out of the oceans, or managing it better back into the economy. So this trade-off of resource intensity, greenhouse gas emissions, and circular economy is at odds with one another. So returning high quality material into the economy does have a capital carbon cost and resource cost. And I think we often come back to looking at the 3 R's, and the first of the 3 R's, which is to reduce waste. It always comes back to that being the one of the most important strategies for achieving a lower waste society, in addition to developing circular mechanisms. From that end, I want to conclude by saying that we are working on developing guidelines, including life cycle impact assessment methods and metrics for understanding the risks of plastic leakage into the environment from the economy. And I think this is actually one of the areas in which life cycle assessment methods still need more development. So I just want to thank the people from my group, who are, some of them are here and online, and looking forward to a great conference today and hearing some more from the other labs and the students, and our industry session this afternoon. So thank you.
Let me just say that I remember the first year you came to Israel. You remember that we met, and I said, I'm so grateful that someone from LCA in construction industry is here. We don't have enough people, and that's the opportunity, right? Not just the challenges, but again, it's dependent on us. So thank you, Sabrina, for introducing your laboratory in the Technion. And now we'll ask our architect, Shani Barad, head of the DD Lab, Disruptive Design Lab, Faculty of Architect and Town Planning from the Technion, to join us. Chat מארגנת את המצגת. Until you organize the presentation, גם התחלתי לדבר באנגלית רק, אבל ויתרתי על העברית. I just wanted to say that I saw Shani for the first time 4.5 years ago, and it was love in first sight, but she didn't know that. And then I asked people about her, and then I asked to meet her. I was surprised to see so many important technologies regarding architecture and calculation and data science, something that I've never seen in Israel. And we're honored that you're here. So thank you for joining by Zoom in here. Shani, the stage is yours.
Thank you. I don't know how to match the expectations now. Okay. So first of all, yeah, there's an echo. Okay. So thank you, first of all, Adi, for initiating this, and also for Vered and Sabrina for really what started as a discussion and is now becoming something much more creative also for us to push forward. So I will introduce the work that we do at my lab at the Technion. It's a quite young research lab, which is called Disrupt Design. And first of all, I'm an architect and a designer. And I wouldn't say that circular economy is the title that I've ever thought that would be somehow associated with the work that I do. So sometimes you actually stumble upon research topics and interests through the work that you do, and mainly, I think, through collaborations. Disrupt Design is basically a lab that I initiated that first of all utilizes my experience from practice, as I first of all was a practitioner before I became an academic, and mainly discusses applicable research which connects industry and academic research. And the most important thing in any lab is, of course, the people. So this is the wonderful group of people today in the lab. We're 12 people and growing to 14 in October. And I think that when I have to try to explain the three main aspects that I would like to put forward today, both for discussion in terms of academia, so the research session, but also for practice, the first one is the development of manufacturing workflows for emerging materials. So somehow the understanding of when we discuss bio-based materials, biodegradable materials, recycled materials, basically what we need to understand is that we're discussing emerging materials. These are the materials of the future, if we want to say it plainly, and the materials that we as designers have to understand that we have to take responsibility to integrate within our workflows, and even the way that we start to imagine the materialization of the spaces that we inhabit. Through this agenda, what we do in the lab is we develop manufacturing workflows that go from computer-aided design to computer-aided manufacturing. So developing computational workflows through simulation engines, through the development of manufacturing toolpath, and at the end, the fabrication of prototypes. So we're able to test a complete workflow, starting from an emerging material to the actual actualization of a prototype, which is related to either an element or some kind of prototype that is relevant for the construction industry. I won't go to detail into all of the processes that we're developing. The materials that we're currently looking to is additive manufacturing processes with bioplastics, which you will hear more about today from architect Avraham Cohen from my research lab. Another material that we're currently developing manufacturing workflows for is wood. So moving from the understanding of wood as a modular, right, element of sheets that has to be assembled, to starting to print wood, which is not based on thermoplastic, as usually the materials that we have when we print, but is based on cellulose that enables us to print and also adhese. And this is a collaboration we're doing today with a company which is called Daika Wood, an Israeli startup. Another material that we are developing currently is cement replacements by using living materials. So today we're doing a collaboration with Professor Chezi Kashi from biotechnology at the Technion and his postdoctorate Shai Kirzner, where we're using cyanobacteria and the calcium of cyanobacteria to rigidify sand as a potential building material with no cement products. Another aspect that the lab deals with is looking at circular economy not from within, but actually as a holistic understanding of how actually were the problems that we're dealing today within circular economy, how were they actually generated? So looking from outside in and understanding that a lot of the processes that we as planners, architects, designers, but also in a much more multifaceted understanding, the way that we have developed the construction industry has actually generated a lot of the problems that we are dealing with today. And therefore comes the process of regenerative design. Today, within the aspect of regenerative design in the lab, we have 3 projects, 2 funded projects, European. We're doing a collaboration with ecological gardens in the Technion. Basically, regenerative design changes the weights in the way that we understand our design client. We're not designing for humans, we're designing for multi-species. So humans, animals, plants, microbiomes are all stakeholders within our design. And we're developing this now through 2 regimes. The first one is a computational regime, which we're doing through the Horizon 2020 Ecolopes project. And this I'm doing in collaboration with many wonderful institutions, but also collaborators from the Technion, Professor Grofman and Schwarz, where we're developing a simulation engine to understand the dynamics of these different stakeholders. So in Ecolopes, what we're developing is a simulation platform, which enables informed decision-making for multi-species design. In parallel, what we're doing is 2 more projects. One is another funded project from Eurotech, and another one is a collaboration we're doing in the Technion with the ecological garden, where we are coming from a material perspective. So this is a collaboration we're doing with Itung, where we change the pH levels of the formula so that we have a pH neutral material, which enables us to grow both vegetation and also to start to develop habitation for different types of species. What you can see, for example, over there is the neutrality test that took us quite some time to develop. But also here, what we see is that we come back to the same computational workflows from cut to come that we develop also at the material scale, where from the simulation, we develop the tool path to the actual fabrication at the lab and the actual prototype that then starts to become the first experiment that we lay out in the ecological garden. And the full wall, which will be 10 meters by 3, will be laid out in August. And then the third thread that the lab is looking into maybe comes to the end of the workflows I was showing before, so more to the computational design and data-driven design, which is workflows and tools for informed design and planning. In the lab today, we're looking at different scales of decision-making processes for designers, so tools for architects, but also for decision makers and policymakers. And this is really highly rooted also in work that I was doing in practice with Chaga Architects, together with my partner, Gary Friedman. Just to give a bit of a glimpse of what we do, for example, here we're developing a decision support system at a municipal level, testing different clustering algorithms to check confined beams. So for example, if you see Tel Aviv, on the one hand, we see the neighborhood subdivision as given by the municipality. And what you see in the clustered in the colors are actually the neighborhoods that are derived from questions that we ask about the city. So how is connectivity modulated within the city? How is the distribution of schools, kindergartens modulated within the city? And we're able to actually extract real data and understand the distribution and not the bias that comes from given municipal boundaries. Another aspect is, of course, working with SRS, so with sustainability rating system, and starting to automate what doesn't exist today, especially in within Israel, with המועצה לבנייה ירוקה in שכונה 360, enabling architects to actually understand sustainability rating system benchmarks as part of an optimization process within a design and a computational workflow. This is the work that was done by O. Moskovich, one of my master students, that will be presented tomorrow in another symposium that Yonatan Etanyan is doing tomorrow at the Teknion. So this was in a nutshell 3 threads that the lab is looking at. Thank you.
Thank you very much, Shani. About 3 years ago, I came to Dr. Vered Blas and shared my idea for my PhD. And she was surprised because I have 20 years of experience working with government entities and startups and industry. And I've teaching here in the Tel Aviv University and in different academic facilities. But I never thought I'll do my PhD on illegal waste dumps. And this is something that I'm passionate about, how to do a life cycle analysis of those illegal waste dumps. Can we save energy, water, electricity by treating those illegal waste dumps? And that's my challenge. And that's a problem globally. It's not just in Israel. So thank you again, Dr. Vered Blas. I'll read all the title. Head of the Innovation Industrial Ecology Lab from the Department of Environment Studies, Tel Aviv University. Thank you again for joining.
Thank you, Adi. Okay, so I'm talking a few minutes about my research and perspective in my lab. As Sabrina said and Shani said, the lab is nothing without our researcher and master students and PhD students and postdocs and programmers and research assistants. It's a very lively environment, I think, for all of us. The construction area is just one part, or the sector is just one part of my research agenda in big. Today I will focus mainly on the construction side, but I would just say that we research circular economy in large, so waste management, specifically electronic waste, the contribution of sharing economy and closed loop supply chains and operations, sustainable operations, everything at the end has connection, of course, to circular economy. And we also work in the area of basically developing new industrial ecology tools, so methods and tools to better do LCA, to skip doing full LCA and using machine learning or other concepts to generate the relevant data locally. So in my lab, we're trying to apply life cycle thinking approach to both production side and consumption side. And I think that's also the beauty of what we do here today, because, if you already saw Shani's work and Sabrina's work, it's at time, it's a very material specific or technology specific. And then what happened, and generating ground data, which is really important, then the things that Shani talked about with the production processes and other innovation. And then in my lab, we come more from the bigger picture approach. So how can we take this data about the new technologies, the new materials, the new business models, and see what happens if we take them and implement them in large, how it will contribute to circular economy, what does it mean from consumption side, from production side, and try to look at it at system approach. Many times we look at the same topic from micro and macro perspectives, so can I have a group of students working in the construction area, one would be for a very specific new recycling technology, and other one will do an analysis of the next 30 years of the construction sector in Israel and how the GHG emissions or the materials consumption will be. And we will see some example today. From day one, the interdisciplinary approach is a must and is a key in my point of view. And we collaborate with many different research groups. Some of them are on the operations side, some of them on the specific technology side, some of them are from consumer behavior side. And it's, of course, sometimes very challenging to integrate everything together. So our focus, if I need to kind of summarize it in a one sentence, is we're trying to combine environmental quantitative assessment and system thinking, but complement it with a qualitative and quantitative social science-based understanding of people and organizations. Because we can have all this great innovation and ideas, but at the end of the day, someone needs to implement it. Right? And it's about the people, it's about the organizations, it's about the government, it's about the challenges and barriers that we have. And if we really want to leverage and make it happen in reality, we must take into account all those challenges. So that's where also the challenge is, exact sciences versus social sciences and combining the methods. And it's an ongoing challenge, but very, very productive, I think. I like to talk about innovation in circular systems. And this is part of, again, moving from this theoretical part to the practical part, okay? So for, I would say, 5 to 7 years now, we talk a lot about theory of circular economy in Israel. What does it mean, and what it will be the benefit, and the social benefit, and the environmental one, and it will also be better on the business side. Everyone is excited, but then at the end, how am I related to that? Tomorrow morning, my business, my research, where do I touch, right? Where do I make a difference and actually make it happen in reality? And I think that's where we still have a lot of room for innovation in thinking about circular systems, and not only at the end of life, right? So a lot about recycled materials and how we keep using the resources efficiently, but also much earlier in the value chain. Right, so from the design and R&D and some of the concepts that you saw here already, Shani and Sabrina starting to talk about it, to production processes, to even packaging, right? Every construction material also come in some type of a package, right? So we must take and look into the packaging part as well. Of course, the use phase and how we use the buildings and building as a service, right? All those new concepts that we already talk about, but we are not sure how to really implement. And all of that is, of course, with the need for supportive IT, simulations tools, for building infrastructure, for new recycling methods. So it's all connected, but it's very bombastic and very big picture approach. And much of our research touch on different aspects of those intervention points that I mentioned. So a brief of a relevant work for the construction world in my lab. So the first one is what Adi mentioned, mapping illegal construction waste in open spaces. And we will see some of those examples now, and some of the speakers will also speak about it. So the embedded GHG emission in construction materials at a national level. Sophia will have a presentation soon. Things related to design and building envelopes, and what does it mean from embodied perspective, and energy use over the lifetime of a building, but also things that maybe doesn't look related directly, but they are. For example, having national water system for Israel, the LCA number for that system. Once we have it, the construction industry use a lot of water. Okay, so if we want to generate numbers that are relevant to Israel, we also need to have, for example, local water data for Israel. So you can see it's not always directly, we think that it's connected to the construction industry, but it's inputs that this industry later on will use, and we must have these local numbers. We also started to do some, again, national level material flows that are relevant, and in that case, you will see one example of aluminum, which exists a lot in the construction sector. So one quick slide on each. So this is our mapping with using drones. We look like, we identify with those tools the waste available in open spaces, and then we can say what materials are there, what are the volumes, what are the weights, and then we can put environmental price on it and economic price on it and think, okay, can we clean up our environment in a better, more efficient way? When we talk about the water system, we need to look very large. You know, we have the desalination plants, right? We have everything that relates to moving the water from one place to another, right? Maybe chlorinating or doing other stuff. So we need to understand the full system, and then we can go and look at results using life cycle assessment tools to understand the impact of every cubic meter of water that we use here in Israel. Okay, and I'm talking about tap water. We can play with scenarios, more desalination, less desalination, better electricity grid, but it's something that we can then have specific data to use. The last example is about doing material flow analysis, which again is a much larger perspective than what Shani and Sabrina talked about. This is just one snapshot for a really new out-of-the-oven data that a great group of students generated last semester about trying to quantify the aluminum, the amount of aluminum going around in our economy in Israel. And this is just a small section within the buildings sector. So we can know how much we use, what do we use it for, how long it's there, when does it get to waste, what are we doing with that waste at the moment, do we recycle, do we landfill it, Do we take it away and export it, etc.? Very large scale, big picture numbers to work with. I want to conclude by saying why I see this important, the importance of this conference, but where do we go from here? Okay, and that will lead us to the research and later on to the panel. So first of all, we are really missing data for Israel, real data, LCA data, materials data. We cannot talk in the air, policymakers and people want to make decisions on real data, and we don't have enough real data for that industry. On the other side, the construction industry and the green building industry is one of the most advanced sector in Israel related to circular economy and environmental management today. And this is an opportunity for that sector to even jump farther and generate that data first. We do have cross-sectors trade-offs, right? And we must look at them, right? So I'm using a lot of water in that construction industry. Maybe I can use gray water instead. What will be the implication? So start thinking in a larger perspective and the intersections of those sectors. Materials innovations, which we already heard about and we'll hear more about, is critical, especially for a small country like us, when we bring all the materials from outside, beside aggregates maybe, right? So we need to be very innovative here on recycled materials and also related to weather conditions here. So there is a lot to think about. Local circularity is not a trivial thing, okay? We say, oh, we're gonna recycle and we're gonna contribute. No, maybe your recycled material, no one wants to use it here in Israel and it goes abroad again. So great, we are doing circular economy to some extent, but not local, right? And our idea is how to implement now the local circular economy. So we need to check that there is really circularity potential to happen locally. The use of technology and AI is something that is just starting now, and I think it has a big future here to the construction industry. And I would say maybe seeing the simple design of my presentation versus the Shani, for example, that's, I think, directly related to the combination of design-specific and overall system approach. And so having someone from this aesthetic world makes such an important contribution, but we must look, micro and macro, and we must connect between the dots, because otherwise it will stay as ideas, but no one will implement it and take it to big space and big scale. And I will finish again by saying interdisciplinary, multidisciplinary is so important, and we must progress on that. And this conference today is just one step to try to promote that thinking. We need to do better in academia, but also in our connection with academia, to the industry, to government, to NGOs. It's a topic for everyone to work on together. So I will conclude by that. We will move to the researcher session. So we have 6 students presenting. Adi will present each one of them. For the people on the Zoom, we will take questions at the end. So if you want to ask something, just write it in the chat. I'm monitoring the chat. And then, of course, here in the audience, we will have, depends on the time, we will have a short discussion time, and you are welcome to wait with your questions to the end, and then we'll have a session on that.
Thank you very much, Vered. When we decided to do this conference, we asked different researchers from different academic facilities to join us and present their research. So I'm honored that we have representatives and researchers from Technion, from Ben-Gurion University, and even from abroad. But first of all, we'll have the stage for Sophia from Tel Aviv University. Who moved my materials? Dynamic analysis of material flows, talks, and GHG emissions in growing Israeli housing sector by Sophia Igdalov, Tel Aviv University. I'm so excited for you. The stage is yours. And again, 10 minutes for each, and questions at the end of all those research presenting.
Okay, so hello. And thank you for the opportunity to present here today. So this research was made as part of my thesis degree here in Porter School in Vered's lab, also with Tomer Fishman, and focusing on the residential building sector in Israel. The main question this research aims to answer is there a win-win situation where we can which will allow us to consume less materials and reduce the GHG emissions at the same time? So why did we choose to focus on the building sector? First, the building sector responds for about half of the raw materials consumption in the world. The production of these materials causes a significant amount of GHG emissions as well as air pollution. And of course, we cannot ignore the fact that huge amount of waste generation, the huge amount of waste generation during the end life stage of buildings, that more than a third of it is disposed in open areas in Israel. At the same time, I guess most of us heard about the housing crisis in Israel. To solve it, to deal with it, the government developed an ambitious strategic plan with targets for new added housing units every year until 2050. According to this plan, the housing units are expected to double between 2019 and 2050. According to this, but what will be the environmental impact of this plan? As far as we know, nobody asked this question. And this is exactly the aim of this research. So the main three goals of this research are estimating the future material demand needed to satisfy the growth in the housing units, comparing between the different strategies in order to reduce the demand, asking what can we do about it, and estimating the impact of its impact on the life cycle GHG emissions. How did we do it? In a very general alliance. So first, our data is based on vintage added housing units data that we took from the CBS and the future added housing units based on the governmental plan. On the basis of this, we use MFA model, material flow analysis, to calculate the material consumption, while on this research, we concentrated only on concrete and steel. The last stage was using an LCL model to calculate the life cycle GHG emissions as resulted from the production of these materials. In order to compare between the materials efficiency strategies, we defined different scenarios. Today, we'll present just 8 out of 18 scenarios that we used in the full research. So the first differentiation we used is between the average size of the housing units. The black column represents the average size of the housing units today, and the pink column represents the minimum housing unit size needed to keep the current life standard. Based on this, we developed the technological scenarios. So first, the baseline scenario, where only the size of the housing units changed. On the basis of this, we added the technology. So in the lifetime extension scenario, we differentiated between the average building's lifetime, 100 years in the pink scenario, 75 years in the black scenario. The max recycling scenario differentiated between the share of recycled materials for concrete and for steel, and the material substitution scenario, where we assume that part of the concrete buildings will be replaced by CLT, that means wood buildings, in 2050. Now, the numbers, the targets in each one of the scenarios are based on the literature. And yet, I'm sure that some of you will have some rejection, some thoughts about the number themselves. So before we are starting to argue the numbers, it's important to say that we don't recommend at this stage the implementation of any of these scenarios. We are playing a game. Let's assume what will happen if. For me, the most important thing that you can take from this presentation is that there is a very powerful decision tool that can be used by policymakers as well as private companies in order to transform to a more circular economy. Saying this, let's move into the results. So on the left side, we can see the results for the black scenario with the bigger housing units, and on the right side, the results for the pink scenario with the lower size of housing units. First, we can see that reducing only the size of housing units without any implementation of any other technology allows us to stabilize the demand. We can see it here in the baseline scenario. It stabilizes the demand, in this case from concrete, and is much more efficient than any technology we can use in the other scenario when the size of the housing units is bigger. Also, we can see that in both of the cases, it takes around a decade until we can see any reduction in materials consumption. It takes time. And of course, it's very clear that the CLT scenario presented by the green line is the most efficient scenario. combined with the pink scenario with the low housing units, it allows us to achieve in 2050 the same demand level as was in 2010. Here we can see it, that it's the same demand level for concrete. And that's although we are we are building much more housing units every year compared to 2010. Now, probably you tell yourself that it's nice, but the decrease in the demand for concrete is at the expense of the demand for CLT. One increase while the other decrease. So obviously you are right, but here we can see, obviously you're right, but you can see that the exchange rate is very small. The concrete represented by the red color and the CLT represented by the gold color, the exchange rate is very small. We need much less CLT to replace a much bigger amount of concrete. Now let's talk about GHG emissions. So here we can see again the comparison between high and low size of housing units. In compared to the material demand, in the GHG emissions case, the recycling scenario achieved the best reduction. The recycling scenario represented by the orange color, 22% here, 43% in the pink scenario, in 2050 compared to the base scenario. And talking about the waste production, and when we differentiate between steel and concrete here and steel here, we can see that most of the GHG reduction is due to steel recycling, while in the concrete's case, the GHG emissions reduction are even increased compared to the baseline scenario. Now, talking about the demolition waste, we can see that reducing the size of the housing units do not achieve a significant reduction during the scope we are looking on. Maybe it will achieve better results if we will look on 50 years later. The recycling scenario achieves the same reduction as the short term, but the life extension scenario represented by the purple line is more efficient in the long term. So in conclusion, when we are trying to answer is there a win-win situation? Is there a scenario that achieves the best reduction in all the scenarios? It really depends on the variable that we are looking on. So if we are looking on the demand for materials, we saw that the CLT is the most efficient one in reducing the concrete. But looking on waste, there is the lifetime extension, which is more efficient. And looking on the GHG emissions, the recycling mainly of steel is the main efficient one. But changing the lifestyle in this research represented by the size of the housing units achieves a higher reduction than most of the technology scenarios. The long-term planning is very important in this case. And we saw that if we will be able to plan our materials consumption and all the system for the long term, we can achieve a very big reductions. And the action opportunity window is short. If we want to achieve a reduction by 2050, we have to react now because it takes time to the scenarios, to the technologies to start to react. Thank you very much.
Okay, that was really interesting. Thank you very much, Sophia. You'll have all contact emails of all the researchers, so you can also take a photo or take a screenshot. את רוצה רגע ורד לסדר את המסך שנזיז? So thank you very much, Sophia, for the great lecture. It's also an opportunity for saying that I'm coming from a geography background. Sophia from database, right? Let's say computer in general, not geography. So you see multidisciplinary researchers coming from different areas. The next research will come from the Technion. Thank you for joining us. Musab Maraka from the Technion talking about BEAM, material passport to support building deconstruction and circular economy. Musab wrote many articles. You need to read them. It's really fascinating. Thank you for joining us.
Good morning, everybody. My name is Musab Maraka. I'm currently a PhD student at the Technion. Today, I will give a presentation about BIM material passport to support building deconstruction and a circular economy. So the agenda for this lecture is introduction, literature review, the objectives and aim of this research, and the research methodology, presenting a case study, and discussing the research limitations and challenges and the contribution. So construction sector is one of the most important sectors in countries' economic. Buildings are major consumers of energy and emitters of greenhouse gas emissions. So according to the International Environmental Agency, building construction and operation is responsible for around 36% of global energy use and 39% of greenhouse gas emissions. At the beginning, I will give a brief description about some of the terminology that I use them in this research. BIM, or Building Information Modeling, which is a verb or adjective phrase to describe tools, processes, and technologies that are facilitated by digital machine-readable documentation about a building, its construction, its operation, and its performance. It has several benefits like maximized efficiency, reduced errors, better insights into projects, and less risk and wastage. Life cycle assessment (LCA) has emerged as a framework to address environmental impacts in multiple industries. The material passport, which is a qualitative and quantitative documentations of the material composition of a building, displaying materials embodied in building as well as showing their recycling potential and environmental impact, which in turn gives them values for recycling and reuse. Results obtained from the material passport are the material distribution within the building, the share of recyclable materials, and the total amount of greenhouse gas emissions, acidification potential, and the primary energy intensity incorporated of the materials. So the aim of this research is to investigate the use of material passports as a system for digitizing the material composition of new buildings, to facilitate their eventual future disassembly and sale to secondary recycle markets, and investigate the use of BIM as a tool to support the material passport. The main research method used is a case study. We selected for this study a big commercial project with area around 50,000 meters square. In this project, some innovation management like lean implementations and BIM in the big room are implemented in the project. Around 27,000 meters square of curtain walls cover this building, which mainly from steel and aluminum. So the methodology for the compilation of the material passport, we use the BIM model as a database for all the materials used in the project. We schedule these materials and classify them to concrete, partition wall, which have different types like concrete blocks, gypsum blocks, etongs, flooring for different types, the curtain walls. And after we got all these quantities used as an input to build an LCA model. We used Gabi to build the LCA model. Also, in order to make this LCA model, we need to get some characteristics and the properties of the materials. So I collected a lot of data from the construction control department, the main contractor who constructed the building, to identify exactly the data sheet for each material. Also, we calculated the waste during the construction phase by subtracting the actual delivered material from the actual build. And we classified the material based on their end of life to recycling, reusing, to give them weights. And the results from the Gabi software was the global warming potential in terms of greenhouse gas emissions, acidification potential, and the primary energy intensity. This figure shows us the process flow diagram. I took this as a screenshot from Gabi. We can see that for each element, we see the material, the input material, the type of the transportation, and the type of fuels used for each transportation. This table summarizes the characteristics for the materials used in the projects, like the lifespan, densities, recycling weight. This table also summarizes the input data at time 0 and at time 100, which see, like, for example, the concrete, because the concrete life cycle is suggested to service for 100 years, so it will be the same. But for example, some other materials, it should be replaced twice, triple, 4 times, depending on their life cycle. These two charts summarize the results of shear materials at time 0 and at time 100. We can see that the concrete materials are the dominant materials at time 0 and at time 100. And the other materials used in the projects represents around 10 to 15% comparing to the concrete. This chart shows the accruing masses during the life cycle of the buildings during the 100 years. The majority of the buildings will be replaced at years after 40 years. I think I took a conservative approach in this way because sometimes they make renovations at the year 10, 15, 20, they change the decorations, but I used, like in my study, the maximum service life for each material. This chart summarizes the global warming potential at time 0, and this is summarizes at time 100. I calculated the global warming potential in terms of kilogram CO2 equivalent per functional unit. The functional unit in our study is 1 meter square of finished building. So as a conclusion for this case study, the concrete material is the dominant material at time 0 and at time 100. The importance of the material passport is in showing the embodied materials in the building during the whole life cycle. So it can help in optimizing, it can help the designers in optimizing the materials that have low recycling potential and have a lot of hazards on the environment. Also, it allows completing the material flow analysis and select the best methods to process each material at its end of life and to which secondary market it should be delivered. After that, I studied another 4 different residential construction projects in the area of Tel Aviv. These projects have different scopes with different areas from 52,000 meters square to around 29,000 meters square, but are typical residential construction projects. This table summarizes the amount of concrete block, e-tongue, steel, gypsum block per meter square. Like I got all the invoices from the construction company for all the materials delivered, and we normalized them by meter square. Also, I quantified the amount of waste per meter square and in terms of meter cube by calculating how many trucks delivered from each construction project in order to see how much the waste generation during the construction phase. This chart shows a comparison of steel material intensities to the literature comparing with other countries. We can see this is the residential construction project and this is the commercial building compared to other economic in the world and where we located. Also, this is show the same things, but for the concrete. However, I hardly find any previous data about high-income Middle East buildings. This is for the commercial building because it's not a typical commercial building. It's actually iconic building. This figure estimated the inflows for the construction based on the results that I got them for the different residential construction projects. We can see that after I derived all the results from the different residential construction projects and we used the statistics for the number of the area of a built floor area from 1995 until 2021, this showed the minimum and the maximum amount of million tons of concrete, gypsum block, and steel which used in the construction. At the end, there are some limitations and challenges for this research. The first is that getting data from construction companies to calculate the material waste during the building construction, because the construction companies, they don't want to show how much they generating waste, so it's very difficult to get these data. Also, lack of data about characteristics and the properties of some materials leads to make some certain assumptions and relies on data from the literature. Also, when I built the LCA model, we used data from the Gabi, and which is related to Germany and Europe. So this underscores the necessity to create a country-specific database for the materials available in the local market. The scope of the BIM implementations in the construction project, like for example, when I used the BIM model in order to extract the quantities, the BIM model missed a lot of data about, for example, modeling the foundations, the piles, some types of floors. So if you depend only on the BIM model without checking exactly how much the scope of the BIM implementation is, then this will make some mistakes in estimating the quantities. BIM level of details. Like in the majority of the BIM models, there was no detailing for the steel reinforcement, which is the most important material for the material flow analysis and the circular economy. And the discrepancy between as-built and design drawings. And at the end, I think we should develop a system that uses the invoices and document it in the construction company, which will be as a database for the material flow analysis. And thanks very much for your attention.
In the meantime, I'll say again, thank you, Musab, for a really interesting lecture. We talk about it as research to research about the challenges, right, Sabrina, talking with those contractors and waste management projects. Now we'll have Avram, I will call him Avi, Avram Cohen from the Technion, talking about robotic fabrication, workflows of large-scale additive manufacturing components, testing the integration of biocide plastic components. Thank you, Avi, for coming from the Technion from Haifa. We'll have Avi, and then we'll have another two researchers presenting, and then we'll have a coffee break. So thank you again for staying.
Hello, everyone. Sorry for the delay. My name is Avram Cohen. I'm an architect and a researcher in the Disrupt Design Lab in the Faculty of Architecture and Town Planning in the Technion, led by Shani, that introduced before. And today I'm going to talk about bioplastic-based additive fabrication and in more focus about robotic fabrication workflow of large-scale additive manufacturing components, testing the integration of bio-based plastic components. As we meet each day in our routine life, the plastic is a major part of construction industry. It appears as a set amount of repeating modules such as panels, roof tiles, pipes, flooring, and more. The wide usage of plastic derived from its great material properties. However, plastic has its own benefit as a material. We also need to look on the other perspective, and that's the waste. The construction industry is the third major largest industry that generates plastic waste, and more than 40% of it sends to landfill. Three major strategies to help reduce the plastic waste and reduce the carbon footprint has been extracted from the literature review and include adoption of additive manufacturing, the use of bioplastics, and increasing the recycling rates. We are, as designers, has a responsibility to adopt such strategies. Looking at currently traditional main manufacturing methods, they have each one its clear benefits such as efficiency and time. However, all of them are based on repetitive manufacturing process and they are not flexible to changes or can handle a complex geometry. In comparison, additive manufacturing allows us the free geometrical complexity, allows us to reduce the material waste and also enable the adoption to changes. However, it has its own currently disadvantages, such as the limitation of material and integration in the construction automation process. Looking at 8 key industries, we can see that the construction industry is extremely delayed in adopting the additive manufacturing, as we can see in other industries. Following our review on the plastic composite in the construction industry, we can see that polycarbonate and PVC are highly used due to their mechanical properties. Polycarbonate is a transparent visual and PVC is opaque. In our research, we selected materials that has equivalent mechanical properties and yet are capable of printability and are either bio-based and or recyclable. We also cross-reference the materials in relation to printing reference, scale of printing, and fabrication method. Based on our review, we selected bio-based PET-G as a translucent material and alternative to polycarbonate, and PPQCF as an opaque material and alternative to PVC. PET-G, for those who are not familiar, is a thermoplastic, a clear material that can be a bio-based, and also all of its versions are highly recyclable and save its properties after recycle. It has also great mechanical properties, what makes it suitable for printing. The second material, PPQCF, is material that's based on sorted plastic waste. It's a thermoplastic that has a very low carbon footprint, and also more than 50% of the material compound is bio-based. It has also great mechanical and chemical properties, what makes it good for printing and usage. Basically, our design method of geometry is one that emerged from the material choice, computational design, and the fabrication method. Through this method, we are able to give external performance to the geometry, such as structural optimization, acoustical diffraction, weight, texture, visual connection, and more. In our research, we implement this design method to PET-G and PPQCF. Here we can see examples and experiments of building elements testing enhanced performance through the combination of material selection, fabrication method, and computational design, like the design method that I introduced before. To start this process, we first did a material test and aimed to check the material printing behavior on large-scale printing. We used a large 3D printer in compared to common ones, big nozzle diameter, and other printing parameters that bring the printer close to robotic fabrication and will allow us to understand better the material behavior in a large-scale printing. You can see that with the same model, by changing only the printing parameter, we reach different results. For example, controlling the opacity material by changing the temperature and the amount of material extrusion. Each one of the material behaves different and demanding different setup until finding the right parameter to print it in a large scale. These experiments allow us to understand also the geometrical limitation that emerge from the material printing behavior. After understanding and get to know the material properties printing behavior, we step forward to set the robotic fabrication workflow. The workflow divides to 5 phases. First is the parametric design model. Second, the performance simulation and the optimization of the model. Third, the final computational model that will be the base to the fabrication process. Fourth, the robotic program and fabrication simulation. And fifth and last is the robotic fabrication itself, the printing. This workflow, we also call it, as Shani introduced before, from CAD to CAM. As case study, we took an acoustic performance. We set a room that has a reverberation, which is a common acoustical problem that refers to echo due to its size. We can see the room acoustical properties and the recommended ones that we aim to reach with the design of the element. In addition, we based on a rule and some rules that our design based on our parametric design. The parametric design allows us to create many iterations and check numbers of design possibilities by changing parameters in our design. Each iteration runs under acoustical simulation. The results compared to results with empty room. After that, based on the set environment and the performance result of each iteration, we could choose the one with the better performance. Here it is. This model, with its performance result, is now used as a base model for fabrication process. Now it's time to move over to the production. Development of fabrication model involves 3 development phases: design the global geometry, decide material distribution, planning the toolpiece, which means what order material will distribute. 3 major benefits of design as a toolpath are the ability to control the structure, the weight, the adoption of the model to the printed material. In fact, through our toolpath design, we feed the geometry to the material we select. So we have the model. We are separating it to walls, shells that made from changing section, and infill that will support it. You can see the dynamic and the change sections through the model and change the support according to the section. Looking closer on a top review of the toolpath, we can see how each layer has the dynamic change due to the layer section, and it changes from layer to layer. This dynamic and flexibility cannot achieve by any other fabrication method but additive manufacturing. In the end, we set the order of distribution material. The computational fabrication tools allow us to evaluate and set many printing properties, such as robot joint speed, amount of material deposition, what time of deposition, type of movement, and also to get signals while the printing process. Following the material test demonstrated before and the computational workflow, we are currently now automating the robotic fabrication process that suits our selected compounds materials, PTG and PPQCF, to enable the printing of a one-to-one scale large building component integrating acoustic performance. Thank you so much.
So thank you very much, Avi. So we heard Sophia from Tel Aviv University, from the lab of Vered. We heard Musab talking from the Technion, from Sabrina's lab. And now we've just heard from Avi, who's a student of research of Shani in the Technion. So that's an opportunity for you not just to hear about the laboratory, but also the impact and research. Most of them, or several of them, are working with government entities, private companies. So if you're interested in learning more, researching more, this is a great opportunity. So we asked other researchers in life cycle assessment and the built environment to join in research and present their research. So I'm happy and glad to invite our next research presenting. Please have a warm welcome to Adam Sabach from Comparative Life Cycle Assessment of Belly Fabric, BYF, Clinker Production. Adam, thank you very much.
Hello, everybody. My name is Adam from the Technion. Currently, I am a PhD candidate under the supervision of Dr. Simon Zhutowski and Professor Sabrina Spatari. And today I would like to present part of my research dealing with comparative life cycle assessment of B-Light, yeelamite, ferrite clinker production. So recent reports show that the global cement production has exceeded 4 billion tons, and this amount is expected to reach 18 billion by the year 2050. Because of the massive scale of production of cement and concrete, this industry is responsible for about 8% of total man-made CO2 emissions. And projections for global CO2 emissions show that if we don't do anything about these emissions, the share of cement is likely to increase to 25% or even more by the year 2050, which is clearly so let's look at where these CO2 emissions are coming from. So these emissions can be classified into three main sources. The first one are indirect emissions that accounts for nearly 5%. The second source are thermal emissions arising from the combustion of fuels and accounts for about 35%. And the other 55% are process emissions or chemical emissions arising from the decarbonation of limestone. And this actually is the main reason why the cement industry is such a significant CO2 emitter. Overall, the production of 1 ton of cement can lead to the emission of 1 ton of CO2. So each of the mentioned emissions can be reduced by several approaches that some of them have been applied by the cement industry. For example, in order to deal with the thermal fuels, we can use low carbon fuels such as biomass and waste materials, but the availability and the replacement level of these materials is very, very limited. As for the chemical emissions, the most common approach is to replace the clinker with supplementary cementitious materials such as slag and fly ash. But as we can see here in this graph, the amount of these materials is much lower than the amount of cement produced, and therefore this approach is reaching its practical limit. So another approach is to capture the CO2 by the cement plant, but this technology is extremely expensive. And the last approach, which is probably the most promising one, is to change the chemistry of the cement and basically developing a low carbon cement that contains less limestone in their chemical compositions. And this can really lead to a real breakthrough or to reduce the chemical emissions. So BYF cement are basically based on different phase compositions. They contain mainly belite, yeelemite, and ferrite. The raw meal of these cements consists of less limestone, but more bauxite and gypsum are needed for the formation of the yeelemite phase. Now, if we look at this graph on the right, we can see that the main clinker phases of BYF contains less lime in their chemical composition, and these reduced lime content can lead to the reduction of chemical CO2 emissions directly. In addition, the low firing temperature of these cements is lower than that of Portland cement clinker, which can lead to reduced fuel consumption and also thermal emissions. So life cycle assessment is a very useful tool that can evaluate and quantify different environmental impacts of a given process through mass and energy balance. And according to ISO standards, a typical LCA consists of four main stages, which are goal and scope definition, inventory analysis, impact and energy assessment, and the interpretation of the results. So the goal of this analysis was to compare the environmental impact and energy demand between BYF and Portland cement clinker production. Here we can see the system flow diagram of both processes of both clinkers. The functional unit of this analysis was 1 ton of clinker produced. The analysis was limited to upstream and core processes. And in terms of LCA, this is called cradle to gate. So the first step in this analysis was to collect data for the inventory. We first assumed that both clinkers can be produced at the same cement plant here in Nesher in Israel. The raw meal composition were calculated based on stoichiometric calculation. And we can see that 14% less raw materials are needed for the production of a BYF, which is clearly an advantage in terms of using virgin raw materials. So the first step in clinker production is the extraction and transportation of raw materials. Most of the materials are coming from local mines here in Israel, except from bauxite that needed to be imported from Turkey. From this graph over here, we can see that the energy for the extraction stage is pretty much similar in both cases. But as for the transportation of raw materials, is much higher for BYF due to bauxite importation. The second step is processing of the raw materials, which includes crushing, grinding, and milling. And the energy used at this stage is derived only from electricity. From this graph on the right, we can see that both energy and CO2 emissions from processing of raw materials are lower for BYF, and this is mainly because less raw materials are needed to be processed. Moving to the main stage of clinker production, which is the pyroprocessing, it accounts for 90% of total thermal energy and 85% of total CO2 emissions. From this graph on the left, we can see that the energy and CO2 chemical emissions are much lower for BYF than that of Portland cement clinker. And this is mainly because the low lime content in main clinker phases. As for the energy and the CO2 thermal emissions, we can see that the values are pretty much the same. And this is because we assume that the same fuel mix and the same kiln is used in this process. The final stage in the clinker production is the cooling down the hot clinker. This stage also serves as energy recovery by heating the cooling air. From this graph on the right, we can see that both energy and CO2 emissions from clinker cooling is lower for BYF than that of Portland cement. And this is mainly because the lower firing temperature that needs to be cooled down from. In this slide over here, we can see the model that was built using the Gabi software, including all the different processes that we saw, such as extraction, transportation of raw materials, processing in the plant, fire processing, and clinker cooling. So this LCA focused on the global environmental impacts with attention to a global warming potential. Different impact categories were evaluated and quantified following the CML method. And the results showed that the GWP for BYF was lower than that of Portland cement. Other impact categories followed this same trend and were lower for BYF than that of Portland cement. However, eutrophication potential values were the same in both cases, and this is mainly because this metric is related to to nutrients emitted to water, while this analysis tends to follow energy and raw materials. So in terms of greenhouse gas emissions, we can see a reduction of 21% for BYF clinker, mainly from the core processes. Lower emissions were calculated from upstream processes and were about 2 to 3%. But we also saw an increase of 14% in emissions from transportation for BYF. As for the energy consumption, we calculated a reduction of 14% in energy demand for a BYF clinker, again, mainly from the core processes. Lower energy values were recorded from the upstream processes, but we saw a 30% increase in energy from transportation for BYF, and this is mainly because of the importation of bauxite. So we saw that the production of alternative clinkers, such as the BYF, is a very promising approach for the decarbonization of the cement industry in terms of both environmental impacts and energy savings. The results show a 20% reduction in CO2 emissions and 12% in energy demand. But we can also say that more research is needed. First of all, we need to test more compositions of BYF in order to get a more clear picture about the impacts of the production of this cement. We also assume that the production of BYF does not impact the economic system of the cement plant or the global market of bauxite. And this actually leads me to the second part of my PhD, which is going to deal with the incorporation of industrial byproducts as raw materials, mainly aluminum, in order to make the production of this cement even more environmentally friendly. Thank you.
Thank you. Yaakov, please join us from Ben-Gurion University. I'm happy to invite Yaakov Florentin from Ben-Gurion. He's going to talk about thermal performance and life cycle energy and carbon analysis of newly developed density gradient hemp-lime bi-compass building blocks. When I went to Ben-Gurion University, I touched and saw and smelled those blocks from hemp. So I asked Yaakov to bring some blocks for you too. So we have samples so you can see more. Yaakov, the stage is yours.
Hi. So I'm going to talk today about the thermal performance and life cycle energy and carbon analysis of a newly developed density gradient hemp-lime biocomposite building block. And it's a research we've done in my PhD studies, along with my professors, David Perlmutter and Erez Gal from Sde Boker campus of Ben-Gurion University. So just as a short introduction, because everybody already noticed, about 40% of the energy in industrialized countries are in buildings, and most of it, or at least half of it, is for space heating, cooling, ventilation, and lighting. And this, of course, translates to a major source of CO2 emissions. So in order to get reductions in carbon emission and carbon footprints of building, it is essential to combine both energy efficiency design in the building, as well as low embodied energy materials, and in particular bio-based building materials, which have low carbon footprint. In addition, as you can see on your right, applying in arid regions or other regions where the temperature fluctuations are high, the daily temperature fluctuations are high, it's essential to combine both high thermal mass materials on the interior of the building and high insulation materials on the external layer of the building to get the moderation of temperature and to get less energy needed for heating and cooling. And this is usually done with two separate layers, usually with very high, with the density variation from, for example, concrete on the inside, which is very high in density, or expanded polystyrene on the outside, which is very low density. So in our PhD studies, we developed a new type of building materials, which combine both high thermal mass and high insulation value in one continuous material, which I also brought a small prototype. It's an old one, but it's small, at least, and not a big one. So you can touch it a little bit later. And it has a relatively low carbon footprint compared to the conventional building materials that we know. So the gradient hemp-lime, and I'll say just gradient from now on, okay, is basically made of the industrial hemp plant, which you can see over there. It's a really tall plant. It's basically cannabis sativa with a really small amount of the psychoactive ingredient, the THC, and it's an agricultural byproduct of the industrial hemp oil and fiber industries. And so what we do is we take the inner woody core, as you can see down there, which has a really porous microstructure, giving it the excellent thermal insulation value, we chop it up, we mix it with a lime, protective lime binder, which protects it, and sand and water, and we mix it, we get a homogeneous mix, and then we applied vibrations in order to segregate the raw materials. The light ones go up and the heavy ones go down. And then afterwards, after it's dry, we place the block on its side, and we'll have the high thermal mass phase on the inside and the high insulation phase on the outside. And that's essentially a density gradient with one side with high density, transition to a low density on the other side. In one continuous material, of course, not two layers. And so the initial thermal performance was tested in a comprehensive test cell experiment, which you can see here, all the test cells are identical in dimensions, but they vary in the material they're made of. So we have the gradient hemp lime. We had other biocomposite, but one of them was the homogeneous hempcrete, which again, it's hemp lime with a homogeneous density of 450 kilograms per meter cube. And the conventional autoclave aerated concrete, which is the main building material that we compared to. We also had among other building materials and bio-based building materials, which I'm not going to include here. There were a total of 13 types of test cells. So even though the gradient, as you can see in the table down there, the gradient have a lower thermal resistance R value compared to the autoclave aerated concrete and the hempcrete. But when we look at a typical summer day, you can see that the gradient actually better moderates the internal temperatures, and this should lead to less energy needed for heating and cooling. But of course, the dimensions here do not reflect the real building, so we decided to spice it up a little bit and to build a small test experimental building, which I've built. It's a timber frame, and you can see on the left before the finish is just the blocks that I made over summer. I put them inside, and here is the south facade of the grad pod, we call it. And on the right, you can see the internal experimental setup where we measured air temperature, surfaces temperatures, relative humidity, and also electricity readings for a small spiral heater, a radiative heater. And basically, there's no air conditioning here. There's a south-facing window for solar gain, for passive heating during the winter, and there is also a small fan for ventilation for passive cooling during summer. And basically, what the results show, and you can see here, 4 months of summer and 4 months of winter, the GRD pod actually maintained comfortable temperature year-round, around 26, 27 degrees, where in summer, for example, the temperatures could reach 36 or even 40 degrees, and also without air conditioning. And also in winter, the temperature maintained around 16 to 18 degrees without just solar gain, without any heat added up. Sorry, I'm a little. So for the life cycle assessment, we had to first to assess the embodied energy and then translate its carbon emissions from the embodied energy of the materials. And here I'm showing just 3 of them. So the gradient, the hempcrete 450, and the autoclave aerated concrete, again with 450 kilograms per meter cube as a density. And I'm not going to go over all of it, but basically you can see that the functional unit per a meter square of wall area, we assess that the hempcrete has a negative value, meaning it actually absorbs more CO2 than it releases during its manufacture in the wall itself. However, the gradient, which has a much higher density, it absorbs some of it because it has the hemp in it, but it still emits about 10 kilograms of CO2 per meter square. However, autoclave aerated concrete was found to be 9 times that amount. So in order to assess the operational energy of the grad pod and the gradient blocks, we first had to calibrate the simulation based on lab tests and based on the measurements from the grad pod. And then we upscaled the simulation to a full residential unit in a multi-story building in Beersheba. And one time we had in the simulation the gradient blocks in the envelope of the walls. And one time we had the autoclave aerated concrete and the hempcrete, which they both perform similar. And so you can see here the yearly electricity consumption of this residential unit, once with a gradient and one with the autoclave aerated concrete. And the gradient consumes about a quarter less of about 25% less of electricity to heat and cool the apartment during the year. And so for the complete life cycle of carbon emissions, we basically add up the embodied carbon from the manufacture of the whole of enough material needed for the whole apartment. And we added up for 50 years the operational carbon emissions due to heating and cooling from either of these materials. And what we found basically is that just by replacing autoclave aerated concrete in the simulations by gradient, we can lower the life cycle carbon emissions around 20 to 30%. So that's it. A really short one. And I also want to say, thank you, that if you're looking for, I just set it up, if you're looking for embodied energy values in Israel, there was a nice report in 2011, I think, by my professors, which you can find online. It's free, and if you can find it, just send me an email and I'll send it to you.
Thank you for bringing the samples, Yaakov, and coming over, Paul. If I'm going to be sick afterwards, okay, yeah. Thanks. Okay, so our last and final research is actually physically in Ben-Gurion University, because he just gave a lecture there, so he's going to join us by Zoom. We're going to have now Achia Livnei from Ben-Gurion University talking about fungal Miscium biocomposite acts as a CO2 sink building material with low embodied energy. Again, when I visit there, I saw the block from mushrooms. It's amazing, really. So I'm really excited to hear from Achia. So thank you for joining. Let's make sure that we can hear you. So just a sec.
So thank you, Adi. I'll be speaking about LCAO fungal mycelium biocomposites that acts as CO2 sink building material. I do my PhD in the Department of Civil and Environmental Engineering in BGU in Ben-Gurion University, and my advisors are Erez Gal from the same department, David Perlmutter from Geography and Environmental Development, and Professor Han Wisten from Utrecht University, Department of Microbiology in the Netherlands. So we already saw the background for construction industry and how much we need to improve it. I will sum it up into what I call the building material conflict, that with the commercial materials that we have nowadays, we need to choose between poor insulation with lower embodied energy and embodied carbon, but we need to pay with the operational energy during the lifespan of the building, or going for good insulation and pay with higher embodied energy and embodied carbon usually, but it will save us the energy during the lifespan of the building. Anyhow, the bottom line is more buildings equals more CO2 emissions. And it's a big motivation to develop new materials that will allow good insulation together with the low embodied energy and embodied carbon. And the idea is to use buildings for CO2 fixation. Is it possible to balance the user? Thank you. So a bit about mycelium materials. The concept is pretty similar to what Yaakov just described of hempcrete, or hempline, just that we use the binder is the mycelium itself of the fungi. So we use natural fibers. It can be hemp, it can be straw, or other waste streams. And the binder is the fungi that grows inside the substrate and bind it all together. A bit about fungi. So fungi, the great teachers for circular economy or circular industry, they close the loop in the nature as the decomposers. They also work in symbiosis with plants, allow the great network in nature, And about the organism structure, so just to make clear that we're on the same page, we have the fungi or fungus, which the main part of the organism is the mycelium, the part that is in the ground. And what we usually see in the supermarket is just the fruiting bodies of the organism, okay, just the way to spreading stuff. I'm working with the mycelium. And a bit about the mycelium materials in the scientific community. So about 10 years ago, there was almost nothing, and it's a pretty new field, which is great because it's like getting into a new planet and understand how things work, but you have a lot of research about and you don't know what will happen if you change one parameter. Some research has focused more on substrates and fungi species. Others, this is from the Technion, so she came more from the designing background. So she searched a bit about local ways to work with, but did really good designs with it. And for example, Mitchell Jones showed really good fire resistance properties when using rice husks as the substrate. And it is not in the way, like it is not found in construction yet. But we have only some exhibitions like the Hi-Fi in the MoMA 2014 or the Growing Pavilion in Eindhoven just 3 years ago. But it's more of an emphasis of we're not there yet. It's used more for packaging now. And my PhD is around taking it toward the construction. And one main thing is to understand if it's worth the effort. Okay, to see what is the environmental impact of the material compared to the common building materials. And that's the part in my research that I was focusing on the LCA of the material. So I made a cradle-to-gate model at this stage for 1 cubic meter of material. And the substrate was a mixture of rapeseed straw and processed cellulose. And the goal was to get the embodied carbon and the embodied energy of the material in order to compare it to other commercial building materials. Generally, the process is we take the millet, spawn it with the fungus, and that's the basic fungal material that we use in order to spawn the other, like the main part of the substrate, which is the agricultural waste, or cellulose is waste from the wastewater treatment plant in the Netherlands. Sterilizing it and putting the spawn, the millet, and then incubating it for 2 weeks. Let it grow, molding it on the same time. At the end, dry it in the open air and inactivate it on 60 degrees for 4 hours. And we have the blocks. So here, just blocks that I put out today. And 2 challenges on this process is to know how much CO2 the plant, like the substrate, sequestered in the beginning, like when it grew. And that's not a big challenge. We took the sample, like the substrates, to elemental microanalyzer and saw how much carbon do we have in the sample. And yeah, basically the carbon comes from CO2. So if we know how much carbon, we know how much CO2 there was in the air, like it took from the air. And the value is 1.59 grams of CO2 per 1 gram of substrate. So that's the negative carbon value that we have in the material. The more challenging part was to measure the emitted CO2 because of the metabolic activity of the fungal. The fungi generally grow like animals in this aspect, the same metabolic structure. They use oxygen, O2, and they emit the CO2. And it's not that easy to measure it. Just there is all kind of measurement that you can try and do. So we wanted first to understand if it's possible if it's significant, sorry. And the method that we used to measure it was to measure the carbon content in the beginning and at the end of the process, again with the elemental microanalyzer. And we grew several samples for 1 week, 2 weeks, and 4 weeks in different substrates. And the final result was really nice. We saw that we have really good correlation between the CO2 that emitted to the air and the weight loss of the sample. So basically, from now on, we can skip the complex measurement of elemental microanalyzer and just weight the sample at the end, fully dried. We know how much substrate we put in the beginning, and we can just say how much CO2 was emitted. After having these two values, we could end up the model, and the final results were embodied energy of 860 megajoules per cubic meter and minus 40 kilograms of CO2 equivalent per cubic meter, which is nice because it's negative, and yeah, it takes us one step forward towards using buildings as CO2 fixators. We don't have a lot of time, but I'll focus a bit on the process. We see the big red elephant in the graph. So the incubation step takes about 73% of the overall energy needed out of this 860 megajoules. And it's not something like heating up to high temperature, it's just keeping the 25 degrees in the incubator. We see that it's also responsible for 43% of the CO2 emissions. So if we will find a way to lower this part, it will be significant. And I want to take your attention to this, the metabolic CO2 emission. We see that 21% of the carbon emissions in the process is because of the metabolic CO2 emissions. So it is significant. We should put it in the models, even though it comes from biogenic source. We have more CO2 in the air. And comparing it to other building materials, so of course that's the only one with negative embodied carbon. And the embodied energy, we see that it's much lower than other building materials, factor of 1.5 to factor of 6. Not that I think that it will replace concrete as is. Maybe it will work more as an insulator, as a filler. And we can see the thermal conductivity of the material, which gets to the values of EPS or other commercial insulators. So we have a really big potential in bringing it into the construction industry. Summing it up, so there we saw that we have negative carbon footprint and low embodied energy building material, potentially building material. We've developed the easy non-destructive method to measure the metabolic CO2 emissions. Pointing out the hotspots will allow us to improve the process in the future. And if we will manage to incorporate it in the construction, it will help us to bring this industry to be more sustainable. Other ongoing research, some trying to grow it on local Israeli waste, and the block that I'm holding here, it's made of palm prunings and grapevine prunings. So it's happening. And of course, to check the how it works in the arid or semi-arid conditions, it's very important because now the research is only in Europe and North America. And ways to reduce the embodied energy and embodied carbon is by reducing the time in the incubator or grow at ambient temperature, the directions that we're checking out. In addition, because I couldn't come to the conference, so I invite you to come to an exhibition in Tel Aviv, in the Artist House in the summer, where the blocks will be put to view. So you are all welcome. Thank you very much.
It's for questions by Zoom or here in the auditorium, and then we'll go for a coffee break. So again, thank you very much. Hopefully you'll bring next time more samples to see mushroom blocks. Achia, best of luck in your research. So let's start in the auditorium and then we'll go by Zoom. I'll ask all the researchers to come. I think that will be maybe easier. את רוצה שנעביר את המיקרופון פשוט? Okay. Excellent. So first question, sir. Just only in English, please.
So hello, everyone. Thank you for the amazing lectures. My name is Jonathan. I have a question for Achia. do you try to quantify how much carbon you basically save from uncontrolled emission of the waste? You say that the mycelium is grow on local waste, biological waste, which is also decomposed and emits CO2 to the air. You can basically kind of add this contribution also to the carbon fixation, no?
If I understand correctly, so I did quantify the amount of carbon that like the plant sequestered from the atmosphere during its growth. So that's already in my calculation. And that's from the assumption that it's pure waste. So no, like taking all the CO2 that would have been emitted to the air if we would have burned it or whatever we do with it. Did it answer?
I'm not sure I understand. You said that you included this contribution in the numbers that you presented. Like how much CO2 would emitted if it will decompose in uncontrolled way, let's say in the atmosphere, in the environment.
Yeah, calculating it, like calculating the sequestered CO2, so counting every carbon atom in the sample as something that would have gone to the atmosphere if I wouldn't put it into my material.
Okay, thank you.
Welcome.
Thank you. I have a question to Sophia, in fact. And first of all, thank you for a very interesting, insightful presentation. One aspect that sparked my interest was when you showed the comparison of the two scenarios with the low and the high housing unit prices. In the scenario with the high or large housing units, the recycling scenario was essentially the best one, but with the lower housing units, it seemed to be very similar to the one with the material substitution. And I was wondering what the reason is for that. Is that due to like different economies of scale?
You're talking about the demand for concrete when you're looking on the...
No, for when you showed the greenhouse gas emissions.
In the GHG. Okay, so it depends on the time that takes to the technologies to enter the economy, because the assumptions are a little bit different, but in the end, in both of the cases, the recycling scenario was the most efficient one in reducing the emissions, because it took to the recycling more time to enter the economy than the CLT. So the impact was a little bit more for the long term than for the short term.
Thank you.
Hi, and thank you so much for the very interesting presentations to all the researchers. My name is Merav Cohen. I'm from the Technion. And my question, it mainly for Achia, but maybe others might find it relevant as well. So we're talking about circular economy here, and some of the presentations were focused on cradle to gate. And I'm just curious as to your approach as scientists. You're developing a material, so it's really difficult to think as you're developing it, you know, what's the end of life or how to design it for circularity. So I'm curious as to your thought process as you're developing a new material. How does planning or designing for circularity comes into play when you're building such a complex new product? So maybe Achia can start, and if any of the other speakers.
Achia, you can start answering.
Yes, of course. I think that with my material, it's really easy. Do you hear? Yes, do you hear or not?
Yeah, we can hear you.
Yeah, okay. So I think that with my material, it's pretty easy. Generally, I'm taking agricultural waste or organics with mycelium, which is organics. So basically, I don't think that I need to put a lot of thought into it. Like, I don't think that we need to design differently. In my case, I think that in less compostable materials you do. I can say that with my materials, so you have at least two solutions. One is that you can compose it at the end, or just throw it in your garden, ideally, or reuse it. Generally, there is still things for the next generation of fungus to eat, so you can use the material. It's not something that I did until now, so I can't say that it really works experimentally, but the idea is that we can use the same like old walls in order to grow fungal blocks, microblocks again, and use it again.
So if I understand the question correctly, we didn't use cradle to cradle, basically because of really high future uncertainty regarding what's going to happen with the building blocks. But basically, it's a biodegradable. Both the hempcrete and the gradient block are biodegradable, and you can reuse it. You can just reuse them or recycle them as you please. We've done it through qualitative analysis, but not in terms of quantitative analysis.
Great, thank you. I would add on that, and we will go to the two quick Zoom comments and questions. I would say that, you know, at least from my perspective, this is a super critical question that must be addressed. However, we see more and more, you know, it could be an academic setup when it be the early stage, or even startups, you know, that are already almost in the market. They envision something about the product which is great, it's biodegradable, it will be awesome when it gets to end of life. But then in practice, the system doesn't work this way, right? So, you know, you see all kind of biodegradable and whatever things. But what is the scenario at the end that this will get to the right setup so it can really disintegrate or whatever? So that's a super important comment, and it must be addressed, you know, when we, especially in the context of circularity, something to think about. But of course, it's not the only aspect. Today, many times we see LCA studies only focusing on the end of life. So putting everything else and just comparing different end-of-life scenarios is already also a very comprehensive to do. And even there are software tools today only to deal with waste management, LCA, or alternative for end-of-life to just model this end-of-life part. So that's something that is important, and more work will be done on that, I'm sure. Quick two questions from the Zoom. Gil had two questions. So Gil, actually, you can unmute yourself and ask them because there's only two. The first one is maybe generic for everyone. The second one you can ask by yourself. But all of you that develop these great materials in practice, how long it will take us until we can see such materials in the market? There is a lot of barriers to getting, as Gil said, to get the permission to work with them, right? Safety-wise and strength-wise and whatever. So what is your anticipation? Is it a few years? Is it a few 10 years? You know, where are we doing on the different materials that we saw here today?
I can answer that I have no idea. I can say that the research is developing really fast. The number of publications is growing exponentially. The labs to work with mycelium is popping like mushrooms after the rain. It's something that is accelerating. And since you already have Ecovative, we really have commercial material, but for packaging, not for construction. So it kind of starting to get the awareness of people that it's possible to use it. To say that when we will manage to get into the construction, it's impossible for me to answer, sorry. But I don't know, I know about a lot of initiatives of people who try to do blocks, whether it's in the academy and whether it's in their farms. I don't know, hard question.
So maybe just to help with the answer. So I would assume that some pilot projects, so at least of some of the new materials. So maybe the pilot stage. Do you have an estimate for that?
Are we talking to Achia or to Yaakov?
To all the presenters with regarding to the materials.
I can answer from our side as a designer, if it's interesting. So basically, we are working with industries and let's say some commercial the industries that develop materials, and we also the problem is more technical, let's say, because we need to adjust the process and everything. But we can see, as I presented, that more and more design projects start to understand what is the responsibility of using those materials. So the limitation is more technical, I will say, than regulatory. But we need to see and to start to make it that it will emerge and be more common in each project. So as a material scope, I think that it's okay because the materials exist and they developed, but now it's the time to understand how to use them.
I can just add one more comment on that. I think that regulations are actually in our favor. So when we see European regulations, they actually are becoming an incentive for commercial industries to come to academia to be able to meet what they know is going to come. So we have industries actually coming to us wanting to help us reach the necessary benchmarks because they understand that it's coming. So actually, it's a very interesting moment, an acceleration, I think, of.
They want to sell back in Europe. We wanted to sell in Israel. So that's something to remember. You know, we're doing great development, and it's not the first, sector that is doing it. We did it with solar, we did it, and we barely implement it later on here. So it's also time to talk with the regulators that they will demand it here. As well. Gil, the last question is for Sophia specifically. So I suggest that you can contact later and ask her. It's about the size of the housing, the scenarios, why we chose that. And it's now time for your coffee break. I won't disturb it with telling you how much water you consume indirectly when you drink that coffee, but go enjoy it. It's 14 liters for every cup of 250 ml coffee that you drink, but enjoy your coffee. And we will meet back here at 11:45 to continue to the industry and government panel.
Hi, everyone. Again, we're in a panel discussion. We're going to talk about theory versus practice, circular economy in the built environment, sharing thoughts, barriers, and opportunities. Again, thank you very much for everyone to joining us after this break. We have a first speaker, Adital Ella. She's the founder and CEO of Createra Earth Technologies, industrial designer, and sustainability expert. I'm so excited that you're here, Adital, because when I visit your factory, I was amazed that these kinds of materials and products can be designed originally, life cycle products here in Israel, in Holon. So thank you again for coming. Adital will talk for 10 minutes, and afterwards we'll have a panel on stage with different representatives from different entities. So Adital, the stage is yours.
So, hello everybody. Wonderful to be with you. As Adi mentioned, I come from the background of industrial design, and to be honest, I started my studies in the mid-90s, and I was very frustrated very quickly because those days of heat beat treat completely felt very, very wrong to my bones. And I was looking for opportunities and looking towards different alleys, how I may learn from the way other societies approached design and approached the material and product culture in a different way in order to find ways for innovation. And at one point, I understood that if we totally eliminate firing out of the equation, there is an opportunity to find a new way. So I started my journey with my own 10 fingers, exploring with my hands, with materials, and how I may learn from different anthropological studies to approach creating constructive materials with no energy investment. And fast forward 10 years later, I'm here with you with a company called Createra. We are producing building products that are as strong as concrete, are 6 times more thermal, and yet are created while saving 80% of the greenhouse gas emissions and 90% of the energy. Although in the beginning, we kind of were in the battle to achieve strength properties, and quite early on, we saw that constructive products are very, very feasible with this technology from a business perspective and a strategy perspective of asking how these products can really enter the market. We decided to start actually with wall tiles. So we decided to start with the more simple solutions that are chosen by architects in order to enter the market as a very young company and create an impact with a few thousands of products and have installations in buildings, commercial installations, even when we are very, very small. So of course, we're tackling all the main pains of the building industry that you all know very well. And our approach is not achieving net zero, but actually achieving zero waste generation, achieving zero fossil fuel dependence, and achieving zero process emissions. So in a nutshell, as I said before, the main difference is we totally do not burn the products. We are also based on minerals. We combine them with natural fibers. And in our production process, we never go beyond the boiling point of water. So we create physical connections instead of chemical reactions in order to create products that are circular in their essence. So they do not change chemically. So at the end of their life, they can either be reactivated to new products. And in our factory in Hulon, where we have both an R&D lab and our production line, what goes at the end of the line goes immediately to the beginning. We add water and it's fully recycled with no harm. At the end of life, it can either be reactivated, as I mentioned, or go back to the original particles in nature because it was not changed chemically in any way. So in this way, we keep the economic and environmental value of the natural resources that we use forever. When it comes to properties, our material excels in compressive strengths, in impact strengths, and of course in thermal resistance. As I mentioned before, if I would drop a Createra tile here next to you on the ground, it will not shatter to pieces like a ceramic product. And its thermal resistance will be quite good, and in some cases it will be as good as Itung blocks. So our technology is patented. We are, of course, taking those forward again all the time as our body of knowledge expands and as our experience with working with non-fired minerals gets broader and broader. So these are some of the installations. We are working with very key construction companies here in Israel. This is a lobby that Tidhar project in Florentine village in the south of Tel Aviv. This is a restaurant in Jerusalem, lobbies in Tel Aviv, and some offices. We have already hundreds of installations, and this is our first product featured in the Netherlands in an expo called Floriade, which is demonstrating the most sustainable products on the market. And we are featured as wall tiles in a bathroom in this building there. The exhibition will be for the next 6 months if you want to visit. So our approach, and as I mentioned, coming from industrial design and as a young designer, after I completed my sustainability design studies in the Netherlands, I understood that in order to really innovate in this field, you cannot just innovate on one part. You cannot just ask about the material. You cannot just ask about the production process. You really have to ask about the entire cycle. So we approach the development process from a systemic solution approach, from the molecule level to the industrial line level. So for your question before, we have guidelines, 6 guidelines of how every choice that we make will affect the environment and people. So we have this analysis that we do. And yes, sometimes there are compromises, but at least we know what are the 6 factors that are the most relevant to how our material will affect the environment during production, at the end of life, and so on and so on. So we are a multidisciplinary team. We have a deep scientific material science team where we created the composite material that I defined before. We created a binder that is fully natural, zero cement binder that allows binding from a physical point of view, and a biocomposite sealer that protects the product. We also created an algorithm that allows us to adapt the technology with the concept of local production for local use to different geographies. And this allows us also to put within the material in some circularity concepts, leftovers from demolished buildings and so on. So we can be both in a technological cycle of creating materials that are based on recycled materials, or we can be in the fully clean biological cycle that can be then integrated in a clean way to the environment. And in addition to that, as I mentioned, we create the entire industrial concept to allow us to achieve the constructive strength without going beyond the boiling point of water that allows saving the carbon in the minerals and allows us to, of course, save a lot of energy and pollution. So based on the multi-level design approach, we are creating the entire industrial concept, and we're using the tiles as the first application to do that. We are operating a pilot production line in Hulon. It operates in a pilot level. It produces about 300 square meters a month. And we are now working towards the first production line that will be in Portugal based on locally available materials there. So we're taking this entire industrial concept and later on applying it together with partners to take this material and implement it into the market together with market leaders in every field. So we're not trying as a small company to open industrial lines and so on, but to collaborate with the people that are already on the ground that are looking for innovations. The ceramic market today is crying for solutions because of the rise of the gas prices that are becoming a real threat on this industry. And we see ourselves as a lab that develops fully circular, sustainable solutions that are then implemented into the market with partners on a licensing agreement. So we are, as I said, fully marketing the wall tiles now and are already in R&D of the next applications, which are outdoor claddings and building blocks. In the ceramic market, we are tackling this number 4 kiln that we want to take completely out of the equation and integrate within the factory instead of it, the whole process that allows us to create low carbon, zero emission products. And we are also aiming for a very competitive price. So we want to change the idea that in order to buy environmental products, you have to pay more, but instead we want to support a reality where you have to pay more on pollutive products. So we are aiming directly to the mid of the mass market in order to show that it is possible and feasible to have people choose environmental and also cost-effective solutions. This is the warehouse of the factory that we will have our products in very soon. And as I mentioned, we're also working on the next applications, the first of which is a full-scale building block that we will have by the end of the year in our R&D lab. And as you see, the difference than the other technologies that you saw, our material works best in a very thin wall. So this allows us to create very elaborated shapes that work in a smart design with the air and the material, and allows us to achieve very effective thermal resistance. And of course, a lot of innovations when it comes to how the block integrates within the built environment, when it comes to weight, when it comes to wall thickness, when it comes to the ability to integrate piping and boards and whatever needed. From a life cycle assessment, you can see that there are very intense emission savings in our block comparing to the alternatives on the market. And on a kind of, when you look at the big scale, you can definitely see a very huge potential of savings when after the material is integrated. Now, somebody was asking before about how long does it take? It takes a few decades, for sure, even for very large companies. But we are trying to shorten it as much as possible with the approach of collaborating with the people that are really thirsty to do the change from within, players that are already very established in the industry. So I was asked to refer to some of the barriers or the challenges. So of course, regulation is an issue. I agree to what was said before. I mean, there is a lot happening to support new products coming to the market. In Israel, specifically, politics are very integrated to regulations, and this is something that we really need to ask how we innovate within. We start from day one with regulation as our way to tackle, so we're already working towards regulations that will support standards and will support the integration of products like ours into the market. And yes, it takes years and it takes a lot of money as well, but it is possible. But you have to plan for it. The second is greenwash. That is, I think, very, very sad. The way a cement company could have a paper packaging and get a green label. I think this is something that we really need to fight against. And this is just an anecdote, but it's very hard to stand out when there's so much less bad solutions that portray themselves to be fully sustainable. And of course, as a young company, the whole challenge of how do you really fund your activities? How do you really create the long-term ability to survive when you still don't have huge sales, but you still need quite some money in order to get to growth? So that's definitely something that we are working on, because as you know, funding goes mainly to web solutions and less to materials. And as a woman founder, I have to show this slide, and the blue one on the bottom is the amount of money that goes to women founders in the ecosystem, and God knows why. So these are, of course, some of the challenges that we are facing every day. And I think the main reality check is just about agreeing to take another step every day, because in the end, it's a journey of a million steps that you have to take in reality, tackling all those different aspects to really be very, very clear about the goal of creating impact. And this is the one thing that was my beacon from day one, and this continues to be my beacon every day. And this is the only renewable energy that my company is really working on. Because in the end, we were taught this, and we still need to find a way to make this a reality in the realm of materials, in the realms of products, just as in the realms of what we perceive as living. Thank you.
Thank you very much, Edital. It was such an inspiring lecture and very important one about the connection between research and industry. So I'm very, very glad to invite architect Shani Baut to moderate this important panel. The panel discussion will talk about theory versus practice, the circular economy in the practical world. So Shani, welcome to the stage. Edital Ela, please return. Also, Ruth Avraham, Director of Innovation and Industry of Israel Green Building Council. Thank you for coming. And we have architect Ran Avraham, head of the Green Building Standardized and Labeling Department in the Ministry of Environment Protection. Thank you, sir, for coming. And the last one will join us by Zoom. The last one will join us by Zoom, Professor Irit Saraf Netanyahu, Vice President of Neri Bloomfield School of Design. She doesn't feel so well, but she's still joining us. Thank you again, Irit, for joining us. So we have Ruth, Edital, Irit, and Ran. We'll have the next 60 minutes discussion, questions from the panel to the audience asking the panel questions, also by Zoom if you have. Thank you very much for joining us.
Can you hear me? Okay. So first of all, Edital, thank you for opening the session. And really, it is, how can I say it? It's not just inspirational, it's almost a benchmark. Right? I mean, to see how we can start from developing the bridge, I think, between a research, or it's always the gap between what is the difference between research and R&D, right? I mean, which is the link between academia and practice. And I think that here we have quite an amazing example of how this bridge can be facilitated. So thank you for that. And thank you also to the other panelists. Maybe we can enlarge Irit.
I am here.
Okay, great. We can see and hear you now. So in preparation for this panel discussion, we had a discussion between the panelists, and we kind of raised a few ideas that we thought would be important to bring up. So these are discussions that the panelists will elaborate, but also if the audience would like to join in with opinions, please feel very comfortable to do that. We're not that formal. So I think maybe the first big word that I would like to tackle is regulation. Okay, and this came, let's start with the difficult parts first. So this came also from the discussion that we saw in the academia. And now I would like to understand how regulation meets. So we have governmental representative, we have a moatza, how do you define an NGO? We have a startup company, and we have an architectural and planning practice with Professor Irit Saraf Netanyahu. So how does regulation meet you, and what are the advantages and disadvantages that regulation actually generates for the acceleration of circularity? Okay, it's a big question, but let's try to address that. So not just as the cons, but also what are the pros of circularity, and maybe just to add, also in a local perspective. Okay, so not just, so whoever would like to start.
So, yes, as a representative of the government, of Ministry of Environmental Protection, regulation is part of the system. It's a very important part of the system because, you know, we believe that to influence, to take the right policy steps, we also need to interfere and to regulate the markets. Regulates can give incentives and direction to the industry. And we saw today in all the lectures, it's very complicated and many stakeholders can influence this system. Designers, architects, engineers, researchers, and manufacturers, of course. We're speaking about materials and manufacturing. One of the main advantages of regulation that it can give a signal to the market how to where the market will go in the next coming years. And one of the big steps that we took in the past 10 years, and it's already in the regulation, was the green building standard. I think until then, there was almost no regulation. I mean, there are a lot of regulation, but no specific regulation that can encourage industry, designers, architects, and manufacturers start to ask themselves the right questions. That a lot of it was in the discussion today: emission, circularity, recycling, end of life questions, and how we improve and encourage ourselves to be better, to affect less and less the influence of the environment. So the regulation of green building is already in the law. It actually started 2 months ago at March 2022. And this is one aspect of regulation. The second one, which states on it, it's standardization. The regulation in Israel for green building sits on the 5281 standard, which defined criteria for green building. But it's a very complicated standard that refers to other standards. So what we discovered in the past 10 years that there are a lot of barriers in the regulation of other standards of materials, actually. Maybe some of you know that most of the building materials in Israel must use virgin raw material in definition. So now we are starting to open slowly all the market standards for cement, for aggregates, for other materials types, and allow by the standard, which is also a kind of regulation, to insert recycled aggregates or recycled materials inside in order to open this field and to develop and to innovate new materials. So these are two aspects. I can continue later in other steps.
So I think there are two levels of regulation that we have to relate to. The first one is the regulation of the materials, or maybe it's the micro regulation. When we talk about the Israeli standard, how it meets and who gets through it and how much time it takes. I think you know it better than I do, how much time it takes to go through all the requirements and to answer it. And the second level is how we create obligation among planners and architects and constructors to use green materials, to use sustainable materials, because today it's cheaper to use not sustainable materials. They are cheaper, they're more accessible, everybody know about them. This is the common thing. And you have to make the extra mile in order to change the perception and in order to change the awareness about this kind of stuff. And you need to regulate it from above in the macro level to create standards like the Israeli Green Building Standard, or to create standards that measure neighborhoods, or tools that measure neighborhoods, like the Shchuna 360, which is not mandatory. It's voluntary standard. It's not a standard, actually. It's an index. So I think you have to think in these two levels all the time: the micro one and the macro one.
Can you hear me? Yeah. Irit, you want to respond?
Yes, I would love to. Can you hear me?
Yes.
Okay. So first of all, thank you very much for inviting me. I feel like a very strange bird, you say, in this audience. Hearing all kind of research, materials, very inspiring. I want to really zoom out from all of that and talk about something else. When theory meets practice in my work, I do a lot of urban design work, a lot of city planning, And I want to share my frustration about all these wonderful researches don't meet reality, mainly because of political reasons, lack of cooperation. I'm planning now a big project of renewal of all 3 neighborhoods on the shore of Haifa. We're talking about 6,000 units, will become 12,000 units, and a big opportunity to do something with a city that suffer a lot from air pollution and problems of disconnection from the sea. So I had a dream 3 years ago with the Green Municipality. I visited Oslo with a wonderful tour that demonstrate how Oslo got the European Green Capital of 2019. And I saw the progress and the process that Oslo came through, mainly because of the wonderful cooperation between all parties. It started with the lectures that we heard there, from the bicycle route planner to the waste company. All of them had the same font, the same graphic of their presentations, which already just show me that they work together, not like anything I know here. And then I heard a lecture by the people who were responsible for the waste, and how they separate the waste. Some of them go to building, to land drying on the bay. Some of them become materials for new products, and some of them used for energy. Nothing is really wasted. So it's nice in theory, but coming back to Haifa, I tried to organize a round table and take the big hospitals of Haifa and the academic. We have 2 big universities in Haifa, to take all the Green Council and the local municipality and talk about cooperation, because without that, no innovation can happen in the city. So unfortunately, it didn't really work out. There's almost no communication between the department in the same building of the Haifa municipality. So we tried to do that by ourselves, the team, the design team. We took industry, we took the academia, we took the people in charge of regulation, and we were the one that could manipulate them to work together. So what we succeeded to do is several things that we are put into the design plans. One of them is to do all the ecological network, to renew it, to have water in the valley that goes to the sea without having them go through pipes, to have a natural landscape in all places that we could, to have bridges, green bridges, to go over the roads and the train that blocks the sea from the neighborhoods. We gave a green basket to every developer to choose from. He had to do either green roofs or active panels, or to have the land with new systems. And we force them to cooperate together, because they have, each one of them has a piece of the plan to construct. And if they don't work together, they don't have the whole system. So we took the developers and we gave them assignments in order to build. We also have a very special local program. We made a plant nursery. I don't know if you call that mishtala. That everything that will be planted on this huge area will be grown on the spot with the children and with the local residents through the years. They have greenhouses, and everything that will grow there will be planted on spot. So we try to do this circular economy also with buildings and with devoting a lot of the new apartments into public residence units, which is really rare in Israel. To do it with a private corporation, it's very hard. And to try to get the people to be involved in this process too. And I'm telling you, it took a lot of efforts. Many of the bodies that we communicate with thought we were crazy and we were looking too much ahead. But slowly, we are trying to achieve at least the goals that we put to the plan. And I'm asking all of the people who are here and having all these beautiful researches to meet reality with influence. We did it with the Green Municipality. We asked them to open up the library for students for knowledge, and they did that. It's a beautiful process and a window to knowledge, but it doesn't happen on the real life of the city planners. And without that, all the beautiful and wonderful ideas will stay on, unfortunately, on panels like that. So I think it's a really call up for everyone to join.
Thank you, Irit. And I think maybe we can jump on your frustration and then try to understand responsibility. Okay, so if we do want to start to be pragmatic, and now we're saying maybe that academia is not the engine for that, right? So we have to start to be pragmatic from the different aspects of each and one of your institutions. What is your responsibility? So how do you frame your responsibility for the dissemination and implementation of circular economy, life cycle assessment? So the different topics that we discussed, how can you make...
Shani, can you speak a bit louder? We can't hear you on the Zoom. Thank you.
Can you hear me better?
Yes, thank you.
Okay. So I was asking an important question, which I want people to claim responsibility and to explain what is your responsibility in dissemination and implementation of both the ideas that came from the research. So how can you make the ideas valuable for the industry and also generate value economically? Because I think that sometimes one of the main bridges is, so I can give you an example from our, when we get funding, we always say, yes, but this doesn't include yet economical feasibility. Let us first try out the material, let's do the life cycle, but wait, we're waiting with the economical feasibility. And the question is, how can industry start bringing academia to actually influence and implement better? Maybe Edital, you want to start?
Well, I was 15 years in academia, and now I'm not in academia anymore. And maybe I will just take one step backwards to your question about standards and connect it to the question about responsibility, because I think in circularity and in all this field that we're talking about, it's about looking 10 steps forward. And it's the same with standards, because if we will wait until the moment that we will have a product ready to launch, then we will have to stop for 2-3 years to do the standards, and that will not work. So for example, with our tiles, this was a few years ago, and with tiles, standards are not mandatory, but we wanted to have the green label. So from the Israeli Standards Institute. And we went to them with our beautiful green products that are greener than probably any alternative on the market that has a green label, if I may say so myself. And they are like, but how do we test it? Right? I mean, who cares if it's green? I mean, all our checklist is about, does it have more than this and this cement? Does it have more than this and this pollutant, whatever? And we had to go through the entire process of proving even analyzing in what way they need to look at our product in order to assess it to be in the end green labeled, because it was out of the scope even. And when we are now doing the process of getting ready with creating the standards that will embrace our building block once it will be out. So again, we are studying the entire umbrella of standards in Israel, in Europe, and in the US that are all very, very different to understand what is the closest one where we can ask for amendments in order to introduce a new material. In most of them, the word cement is compulsory. I mean, in most of the products, the word cement is a basis for even introducing a product to the market. So to your question about responsibility, I think it is about looking in all the different aspects of what it means bringing a product to the market and designing 10, 15, 25 steps ahead to asking how I may achieve a product that is cost effective, and how do I design back? How I may achieve a product that fits the standards, and how do I design back? How I may achieve a product that has a relevant bill of materials from a circular point of view and from an environmental point of view, and how do I design back? And it's all the time looking at the bigger picture of what happens when the products are on the market, and how do you design back to what it means now, to the brief that we are working on. And I agree with what Vered said. In the end, it's a systemic approach. I mean, there is a limit to what we can do. In the end, we need all the people here together in the different scales to create a reality where products like these are really integrated into a circular system that functions. This is way beyond what we can do. We can design the products to be fitting a system. We can design additional products in the end to have a material bank that is fully known and fully circular and so on. But in the end, we will probably not be the ones that will create the collecting and dissemination system and so on. So in the end, it is about looking ahead, designing for a system that would work in the best way 5, 10, 15 years from now, and inspiring government and NGOs and everybody and the Standards Institutes to walk the journey so these two futures can meet before it's too late from an environmental and human point of view.
So I think that the construction market, especially in Israel, is moving really fast because the population is growing, and then we have to build fast, and we need to do all the permits really fast, and we need to plan fast. So we have to do everything fast, but the regulation and the academy is moving much slower. So I think as an NGO, we have to bridge that gap. And we have to raise awareness. We have to promote educational programs. Okay. So as the construction industry is moving really, really fast, and the demand for housing and for buildings, for new buildings is growing really fast. So the planning industry and the construction and the planning industry is also moving really fast. The academy and the regulation move really slow. So as an NGO, we have to bridge that gap. We have to bridge it through raising awareness and promoting all these nice ideas, all these good ideas and important ideas, and to promote educational programs. So I think this is our responsibility in the time that passes between the regulation is becoming mandatory, and before the academia finishes all the research. This is our time to act. So this is one side, and the other side is actually creating temporary indexes. And there we can make mistakes and we can change it because it's not mandatory, because we can try and say, okay, try to use these materials. We can measure buildings. We can do various stuff. And this is actually what happened also with the standard. It was not mandatory for 10 years. And this was the time that we could educate the planning industry. And this was the time when we could promote the idea of green building and doing conferences, throwing meetups and so on. And I think that it's quite the same with technology. I mean, technology is going really, really fast, and then it has a barrier because it has to go through regulation. Then you have to stop, as Avital said. And this is our time as NGOs to introduce the technology to planners, to constructors, and say, this is what's coming. Be prepared. Learn the world of construction as it will look in 10 years from now.
Responsibility. Okay. So I will take all the responsibility for the situation as a representative of the government here. But as you all know, seriously, that it's a very complicated system with a lot of interests and strong driven forces that take everything to different sides. The economy is the most strongest vector that leads everybody, but also things Ruth just mentioned, the urgency to build a lot, to develop a lot, to develop fast, which I think doesn't makes things better for the industry in general, to sit and to analyze the way it performs, the way it influences different aspects, especially environmental aspects, as I think it's part of our discussion. It's also influenced the low R&D in the industry, I guess, but it's also influenced the short time given to planning, to designing, and to think of other ways, alternative ways to do all these practices. So in general, for things that the government does for supporting new approaches, first of all, we do try to update the standards the way it will focus more on performance-based measurements, emissions, circularity, and not only general labels that says I'm green. No, show us how you're green, and trying to set the rules in the regulation, which are already exist in general, but the way to do it right, to be transparent, to develop national databases for different aspects in order to be able to compare performances of different steps. These are also new approaches that we're trying to develop with cooperation with the academy, of course, because we don't have all the knowledge, but the academy can support and ask and dig for deeper question on this aspect that we are interested in. We also influence the markets in other ways. On one hand, we support the local industry there is, for instance, the Yael Center, which is a new center, which it's co-center for Ministry of Environment and Ministry of Economy and Industry, which is not always work together, but in the past years we do it together. This center actually supports in grants and in knowledge the local industry to transform to become better environmental performance industry, to lower their emissions, waste, use of energy and water. In the past year, a lot of the building manufacturing industry is really interested in analyzing LCA processes for their manufacturing. So we see a movement and we influence on it and we support it with money. At the other end, at the other side of it, we also, it's on the table. We are with a lot of discussion with the Ministry of Economy, with the Ministry of Treasury, we do promote the law, the carbon tax step, which will, in another way, put the right prices of carbon-intensive industries versus low-carbon industries. It's on the table of the committee of ועדת הכספים, which is it's very not popular step. If I don't know if there are representative of the industry here, but there are a lot of academy representative, but the industry is fighting it and doesn't want this kind of. But it will come. It will come because the European market is going there, the global market is going there, and if the Israeli market will not put taxes on carbon, then it will have to pay for international economic systems in when we will export our products or when we will want to import products. So it's also better for the local industry to take this tax in part of their calculations. But we also have to support our industry. So it's a very complicated system, as you can understand. But I think the keyword that we promote now is knowledge, transparency, the way to compare products and to educate all the system to start to measure this measurement.
Thank you, Juan. So I think maybe the next question, I have time, Adi? Okay, good. So maybe the next question is, how do we develop performance criteria, right? In order to understand that we are actually generating value, right? In terms of circular economy, which is a huge word that is also being misused quite a lot. And not going to the greenwashing of labeling. So what type of performance indicators do you think need to be developed? And also, how should they be supported? I'll just give an example. When we started looking into integrating material properties, for example, in computational workflows, we found that there's no data set that can actually support our computational workflow and that actually categorizes the materials and is interoperable also with the way that we work. So my question is, again, two-faceted. One, what would be the performance criteria that we, even as researchers, but also that practice needs to be targeting in terms of high-level priorities, and what is missing in terms of achieving these performance indicators? Irit, do you want to try to go for it? You're muted.
Okay, can you hear me? Just in short, the sign or the moment the public will demand it and not the regulation, we'll know we are there. I think a lot of the case studies I examined were done with the public and educating the public. And here, greenwashing is due to lack of understanding, a lack of knowledge. Whenever the public knows what's good and what they want to, acquire or live in, the regulation will not be on the way. Contrary. And this is not the case now here, and I didn't hear any effort except what the Green Council is doing to educate and to explain and to get this knowledge to the people, which demand now some of it. Even if they buy an apartment, they ask for a green code and they want to see the mifrat, whatever you call it in English, the details of the building. And I think this is the only sign that we will understand we got there.
Thank you. Ruth, maybe you want to also address this in relation to how things could be integrated in indexes such as National how the Motsa.
So I think that first of all, I would like to talk about the development of these indexes. And the development is based on transparency. And I was really impressed about the methodology that Musab used, because he got a lot of details about how buildings are being built. I mean, I don't know the English word for it, but כמויות, for example. I think it would be great if we could look at the substances of the buildings, so we can analyze it and actually know what are the buildings are built for and from, and actually see it statistically and develop indexes that based on it. And I think it will help the academy a lot as well. So this is one side of this story, and the other side of this story is developing simple indexes, because the construction industry is moving really fast, and there are a lot of pressure from entrepreneurs, from the public, and also from the government or from the local municipalities to do it fast, to do it and to see results really fast. It's also a political issue. And Ran can talk about it, about the urgency of changing government, of changing local governments, and so on. So we need to develop simple indexes that can be implemented quite fast and quite simply, and that are backed up with apps or simple Excel tables. This is what happens today, but I think tomorrow it will be apps that enable us simply measure our work. So I think it would be the best performance indicator to do something which is simple to use, which is practical, because people on field do not have time. They do not have time to research, to think, to develop, to do R&D. And this is the main challenge of the industry, the fact that they don't have time.
Dan, do you want to? Yeah, let's just, do you want, yeah, okay. So we can open now for the audience. So please just say your name. I will give you the microphone, so also the people. All right. Raksha.
צריך לעבוד ביחד. כולם פה בעצם, אני חושב. קודם כל, הנציג הממשלתי, כי אני חושב שהשלב הבא ממה שאני התרשמתי, אני מהאקדמיה, אז זאת מחקר שמציע אירופה וכל הדברים האלה, זה לקדם סרטיפיקיישן של אנשי מקצוע, זה יכול מאוד לעזור. מהצד של ההתייחסות של המקרו-מיקרו, של ה-education, אנחנו, וזה גם מה שאלה, צריך לעבור 15 שנה קדימה, 15 שלבים קדימה, צריך לחנך את הילדים שהם יעשו ביזנס. הם ישבו בוועדות ויחליטו ולהכניס להם את ה-awareness כבר מקדימה, אנחנו עושים את זה. ורואים, אני בטוח שמה שאנחנו עושים בבתי ספר, נגיד באילת, יהיה לזה השפעה על השוק בעוד 10 שנים, אני ממש מרגיש את זה בכל הגוף. I can say sorry, thank you. I will say it in English again. Just want to say that for the government, that I think that certification of professionals in the building sector is very important today for sustainability skills. And certification means that from the people who are working on the field, the worker themselves, blue collar, what they call, and white collar, which are sitting in the committees, they need to be certified to be there. Another thing that I think for the education part that was mentioned by the NGO, representative was talking about education of the next generation of all of us, and I think that from the micro is really education of children and young people is very important. On the macro scale, of course, we need a governmental scale, but I'm a structural engineer, so I know that there is another scale. We call it mesoscale. It's a Mediterranean scale, okay, in the middle. And this is municipality. In my thinking, I was thinking that municipality have a lot of power to make the change, and the change need to be local for every municipality. So all we need is to convince one mayor, and we can do a lot of things because they can do, how do you call that, that you divided the area, never mind, and they can make some sustainability requests for the Garmushka, the building requirement, and they have a lot of power, and I think that we should go there. And that can work immediately. All we need to convince my lawyer, and just, I'm completing in a second, and just say to Ella that I really understand what she was talking about, and I think that we all should go together. And another advice for myself, coming from the academia, be large to share the right, how do you call that, patenting, the PI, yeah, I think that this is a lot of obstacles, a lot of things are falling between, because we are going to the innovation authority to get money for the government. They're trying to do a lot, and then the company getting bad luck because they think that they're going to get a lot of money, and maybe they should share it with the university. I'm not talking about you, but people are really afraid from that, and it's not too much. And for myself, as someone who wants to advance things, I see that this is one of the tackles that we have. Also, one of the barriers. Sorry.
Well, it's such a complex issue. I agree, because in the end, a company like mine needs to raise money in order to create impact in the world, and we need to collaborate with the biggest players, which require us to protect the IP in order to collaborate with us. And in the end, I think it's the question of impact, because actually IP, which is a miserable, very expensive journey that is not fun and is a very big burden on a company, is a path that, first of all, you share with the world what you do in very high details. So it does open up possibility to innovate and to inspire each other in a way that allows also a company like mine to create the long-term strategy that allows us to bring products to the market. So it's not about being stingy about knowledge, because in the end, even what you write has nothing to do with the depth of understanding of how to work with a material. Everybody that is sitting here would say that. In the end, it is about a craft that is created every day. And even if I write the recipe, it still takes a whole journey to make it happen. So I think it in my case, and and this is my approach. I mean, we are making an attempt to make the most impact we can from the understanding that we have today of how do you take a vision of creating fully circular building products in the shortest time possible without financial backing, creating the best impact in the world. Talk to me in 10 years, I will tell you to what extent we were right in the strategy, to what extent we were not. I do not know. I am doing the best I can in every level of these aspects that we talked about to secure the possibility of collaborating based on the knowledge that we created with the players that can allow bringing this impact to the market as quick as possible. It's a research, it's not in academy, but it's in real life. And I'm happy to share the results every day and what we learn every day. It's not a black and white journey. There's so many levels of grades that you have to carve a path with them.
So I would like to reply about the comment on the local authorities and municipalities. I think they're definitely the key. They are the people that on spot, on ground, they give permits, I think, to most of the buildings in Israel. And they work really hard. And there is a major queue in getting permits. We all know it. It's on the news every second day. And we work a lot with municipality, and we bridge this gap of knowledge between the government and the municipalities, between the planners and the municipalities. And they're also really the key, because they're the one that would make the demands to the planners in order to get a permit. Because everybody eventually they want the permit because this is what will make the building exist or to be built. So I think it has to be heard a lot. Municipalities are the key. They're a major actor, and we need to work with them, and it's really wise and smart on it.
We also work with local municipalities. There are some leading municipalities that help the government to take the green building to a national level. I don't know how much local municipality commitment to change the way manufacturing is being made in Israel, but I think that there are some possibilities to encourage them to understand the importance of it, because at the end they also give permits for licensing of the manufacturers, and they have to make them perform better. But for your questions, Shani, we also have a lot of thinking of how to promote better transparency, databases, and all this lack of knowledge that we all suffer from, because we don't know how we can improve our industry, our design, and all the things we discussed today. I think from what we saw in other countries, government supports academy and combination between stakeholders to promote these kind of databases. I can say that we will promote in the coming revision of the Green Building Standard, which already starts, and I encourage all of you to be part of it and to send ideas and comments. It just started. It will be a few months, maybe a year process, but we will encourage and demand that a certain performance claim will be checked, audited, certified, and also be transparent in a kind of database. We don't want to say exactly the right database. Maybe it will be an NGO database, governmental database, or a common practice, but we hope that it will take the next step to understand the way materials manufacturers do perform and how much we use of each kind of industry. It's not a secret to all of us here that we are really addicted to concrete and to cement, and we have a lot of challenges in transforming to new materials in Israel, different, better perform environmentally materials. It's a big challenge. We saw some examples today of the way to change the influence of different cement, different alternative materials, and I hope that when we will start to measure the performance of all materials, then decision-taking, architects, manufacturers, designers, suppliers will to the right way.
Maybe just Irit, do you want to have the last words also as maybe with the architect planner hat, the people that are supposed to distribute all this good?
Yes, I just want to say you're always talking about top-down, about regulation, about governmental rules, about researchers, but you have to understand that if it doesn't come from the designers, the architects, the common knowledge of the people, it won't happen, because I know I'm dealing with developers. It's very hard to convince them. There is a say, I'll read it to you, in one of the advertisement of, also they said, what used to be innovative madness is now the natural way of thinking. Whenever we got that, to believe that we can innovate, we can dare to try, we can dream, and we can challenge our developers and architects. This is the way to make them, curious and angry to do that. So the process that you described, going down from regulation of the government and getting to the municipalities, we saw that for 10 years now. We got the green code after all Europe is already far behind that. I believe we need to find new ways. I really believe in the collective force of the public to do the change. And I think we should try different ways and not going through all this regulation again. I know I followed the Green Council for more than 10 years till they succeeded. Even neighborhood 360, which I took part in writing that through our projects, took a long time, and it's really almost obsolete now. So what is to be done? I think we should have a circular education or communication to start thinking how it's better to incorporate that and to challenge, like developers with the new products. Regulation won't help here. I know, I'm doing buildings all the time. The most creative process I'm doing with my designs, even buildings, is where the client comes and asks for something innovative. And it's rarely happened, but it happens. And then we start researching. So I think it has to be bottom up as well.
Thank you, Irit. And we have to finish, yeah? So, Laura, Mimi.
Is it Fantomima? I can't hear anything.
Yeah, the question was, what makes people choose our product? To be honest, until the last year, maybe I could, on one hand, I can say the number of projects here in Israel that were chosen because the material is green. So people would refer to kind of the biologic, sensual, natural feel, and that was the main driver. So yes, architects choosing the material from an aesthetic, sensual point of view. But now that we are transitioning to selling also in Europe, the mindset is a whole different mindset. And over there, yes, people are looking for alternatives, and the fact that the material is low carbon with low embedded energy and so on is crucial for them in the decision. 5 years later, when it comes to building blocks, then of course it becomes a whole different story. It's a journey, and we have to plan for journeys and agree to the fact that there are compromises all the time, but we have to plan for the cleanest and the greenest and the most holistic, and yet agree to walk the journey and walk with the consequences that a journey requires in order to achieve the goal that we see at the end of the tunnel, because we're so much involved in regulation and so on with less bad, and we have to really get rid of that way of thinking, but aim for the cleanest and agree to do the steps that allow us to get there. Thank you.
I would like to thank Ran, Ruth, Adital, and Irit for this panel. We could go on, of course. So thank you all. And
thank you.
We now have a guest.
Thank you, everyone. Thank you, Irit, for joining us. Our last guest lecture before our light lunch and sandwiches and vegetables. We have a beautiful, important guest lecture from Dr. Shoshana Sachs. She's going to talk to us from Toronto, Canada, in the next 45 minutes about construction material use and environmental sustainability. I'll share some things about Shoshana so you'll know her background, and we are very honored for her to join us by Zoom. Thank you, Shoshana. Dr. Shoshana Sachs is an assistant professor in the University of Toronto's Department of Civil and Mineral Engineering and Canada Research Chair in Sustainable Infrastructure. She investigates the relationship between the infrastructure we build and the society we create to identify opportunities and pathways to better align infrastructure provision with sustainability. Sachs is a former Action Canada Fellow, sits on Waterfront Toronto's Capital Peer Preview Panel and Metrolonics Project Evaluation Advisory Panel. She was awarded a 2019 Oprah Engineering Medal, the Young Engineer. What an honor. Her research and commentary have been featured in the media outlets such as the New York Times, the Toronto Star, and the Financial Post, TVO, and Wired. Thank you very much for staying with us by Zoom. I'll just tell Shoshana we have, of course, an Israeli audience, but also we have people from abroad joining us. And all of this conference is being recorded and will be sent to all of those who register. So again, thank you for joining us.
Thank you for having me. I'm just going to make sure I can share my screen. Okay, you can see my screen. Great. Well, good morning or good afternoon, everybody. Thank you very much for having me. As Vered mentioned, I run a research group at the University of Toronto looking at the relationship in between the infrastructure we build and the society we create, with the general goal that we should figure out where we're not aligning what we build with what our goals are and do a better job than we've done in the past. This leads to two main research questions. The first is, what should we build? How do we decide on the things that matter when we're making the decision to go ahead with a project or not, when we're going through the process of choosing between options? And then once we've decided on a particular project, how can we go through the technical design, construction management processes to make sure that that project lives up to its sustainability credentials? And the work I'm going to be talking about today feeds into both of those questions and is motivated by two challenges which we're seeing at the same time. One is a major deficit in infrastructure. Certainly where I live in Toronto, we have a huge housing unaffordability crisis. Housing prices have gone up by 40% in 2 years, sometimes quite a bit more than that. Recent reports say that over the next decade, we need to build 1.5 million homes in my province alone. So that's not even the whole country to be able to return to some level of housing affordability. We also have massive transportation deficits, billions of dollars of transit lines, which we've said we want to build, but have never funded. And so just general shortcoming in how much infrastructure we say we need versus how much we have. That would require a huge amount of construction at a scale hasn't been seen in a very long time. At the same time, we have a major climate crisis. For the climate crisis, we need to consume as little as possible. And so there's this tension between having a major need for more construction and a major pressure to consume as little as possible. If we pursued each of these goals individually, we would be putting the other one at risk. And so big question is, how can we find a third way through how to build more while using less in total? To understand the environmental credentials of the things we build, we need 3 pieces of key information. One, we need to know how much construction materials we're using to put into our projects. 2, how much construction energy went into the project, so how much construction energy is used in transportation and on site. And then finally, the impact factors of the greenhouse gas or environmental intensity of the upstream processes that go into making those materials and burning that or generating that energy. And if we know all 3 of those, then we have a pretty good idea of the environmental credentials of at least the upfront, the embodied carbon, or for those who are more technical, the A1 to A5 parts of the life cycle of what we build. In my work, I'm focusing recently a lot on material use. And this is because it's a massive driver of greenhouse gas emissions. Globally, resource use is making up more and more of overall greenhouse gas emissions, both because other sectors are getting better faster than the resource sector, and also because we're using more materials overall and more materials per person than we ever have before. Iron and concrete, which go into making steel and buildings, are the 2 largest drivers of construction resource use are the 2 largest drivers of resource use overall. And the 23% here I'm showing is from 2015. We're already in 2022. It's most likely, based on the projections, that the amounts right now are around 30% to a third of all greenhouse gas emissions are coming from resource use, still with the majority coming from steel and cement, which are going into construction. I'm strongly motivated by environmental drivers, but of course, the world is not everyone cares as much about the environment as I do. And so it's also important to talk about resource use in relation to cost. For every single building that we build in Ontario, where I'm from, but this holds in many other places in the world as well, materials are a massive driver of construction costs, and we're not doing very much to do better on materials. We talk a lot about cost, and we talk about ways of making it faster. Often they say the regulation should be cheaper, but we talk very little about opportunities to be efficient in what we design to make it cheaper to build. One of the most popular ideas in the circular economy is a fairly straight translation of the idea. Things should be circular. We should take the things we used to use and use them again. We should recycle our construction materials. And and people will say that's a way to build things better for the environment, to have less primary resource use. In theory, it could be cheaper because the materials are already there and ready to go. But a basic numbers check shows that this is going to have a pretty limited impact at any point in the near term, because we're building way more than we're demolishing. And even what we are demolished, only some of it can be reused in its current form, and you have to put more energy into it. Often when we recycle things, we have to recycle them to a lower function. So while it's very appealing and it sounds nice, the idea that we could have a pure circular economy and just take materials out of one building and put them into another, that's unlikely to happen, especially anytime soon. So if we go to the classic environmental idea of the 3 R's, reduce, reuse, recycle, recycle isn't going to get us very far. We need to look more at the first two, starting with reduce and reuse of our space. And when those have been modeled by others, we find that if we can do a lot with efficiency, that we can get down with a big efficiency effort, at least to the 2-degree goal, if not quite to the 1.5-degree goal, as long as we start taking efficiency really seriously. And in this paper, they looked at things like lifetime extension, they looked at lightweighting design, and a lot of things in theory, but with no particular goals or guides about how to do that in engineering practice. So that's what this work is going to do. The main obstacles to doing better on material efficiency is, one, we have a really poor understanding of how much materials we use in the things that we build. We don't measure it. We tend not to keep very good records on construction sites. I used to work very closely with a contractor, and one of the first things I had to ask them was, okay, you built this building, how much concrete did you put into it? And they thought it was the funniest question anyone had ever asked them. They had no idea. They had never kept records. They couldn't even really do a close estimate. It just wasn't part of how they measured things. And then we also have all kinds of norms in the way we design and build things that leads to more material use. Early in my career, I was a geotechnical engineer. I worked on the design of metro stations, and I used to design 1.2 meter diameter, 50 meter deep piles, which cost my yearly salary, one pile to build. And we'd be putting sometimes hundreds of them in the ground for a project. And I knew that with a little bit more design, we could save more materials. I always wanted to go to our client and say, give me an afternoon, I'll save you some piles and we can split the difference on how much it costs. They could save hundreds of thousands of dollars. I could get rich. Of course, I didn't want to get fired, so I never did that. The potential dramatically exists in the things that we build. So coming to the research question specifically, one, can we understand better how much materials we're using? And once we understand how much we're using, can we use that as an evidence base to do better? And specifically in my research, we look at form-based drivers in terms of what types of buildings we have and how they're arranged. Because if we can use form to be materially efficient, that's a technical, we don't need any new technical tools to do that. We have the engineering capacity, we have the construction capacity, it's ready to go. We just need to have the policy and the legality to build in ways that are form efficient. In Canada and in North America for a long time, a lot of different types of buildings have been illegal to build. So if you see all of the ones here in color, in most of North America, it is illegal to build buildings like this. And there are now big pushes to make it more legal. But we've been very limited in the types of forms we can build. Most buildings are single family detached homes, so freestanding homes on their own plot of land, or at the other end, we tend to have high and mid-rise condo buildings or apartment buildings, but almost nothing in between. So in our ongoing research to answer the first question, how much material we're using, we've been gathering construction drawings from as many people as will share with us. In Canada, there's no public record of construction drawings that is available for research. So we've been gathering from private companies, from engineers, architects, builders, owners, and getting as many copies of drawings for built buildings as we can. Then we go through all of the drawings and we do material takeoffs. We use a bunch of different tools to do this, but calculate the volume and the quantities of materials in the buildings and their type. And then to make the whole thing manageable, we organize it in a big database according to uniformat and master format, which are construction management ontologies that already existed that are widely used across North America for building construction. And so if you're not familiar with material takeoff, this is the basic way it's done. We have a drawing. We measure the dimensions on the drawing of an element. So in this case, the height and thickness of the wall of this 2-story building. And then that was an elevation. We can look at it on a plan and see how much of that wall exists, multiplies those together, and we have the volume of the wall. It's obviously more complicated than that because there are often openings or exceptions, but the basic idea is just measure it off the drawings, and then you know how much you have. It's a very time-consuming process. It takes about 6 weeks for people to do their first building. And then after that, between 40 hours to 150 hours per building, once people have been trained up and get the hang of it. So it's not fast. The uniform and master format, the codes we're organizing by have a nested structure, which can give a lot of detail on the element and the type of material used. So in uniformat, you have 5 categories, where at the top level, it might be something just as this is in the structure of the building or in the foundation. But when you get down to the bottom level, very detailed of what type of part of the structure or the foundation it is, which means we know exactly where in our buildings our materials are going. This is a pretty big difference from most ways materials are calculated for buildings, which are usually done at just this is how much material was put in the entire building. Master format is quite similar. It has 5 categories where it's more detail about the material itself. And so what we're seeing here is that at the high level, you might have something as general as concrete, but at the detailed level, you would know very detailed what kind of concrete you're using. And so for every measure we take, we develop, I think this is a 40-digit code, where the first number is just what number it is in our database. Then it says where in the world it is, what type of drawings we were doing in their construction year, which is helps give an idea of how certain or uncertain the data is, the type of building, and then starting here where we have 0B1, where in the building it is. So 0B1 would be the first level basement. And then the uniformat codes down to level 5, the master format codes down to level 5, the unit, and a measure of uncertainty, where 1 is it was measured on site, and 2 is where we're more often, which is it was measured from drawings. And the whole thing is nested together, which lets us chop up our data in a bunch of different ways. We published our first 70 buildings in February. And when we use the data to look at where in our buildings all of the material was coming, and this is across 70 buildings of different types, we saw that about half was in the superstructure, with the most amount of materials going to the floor decks, slabs. And a big chunk of the other material was in the substructure underground, which is shown here in light blue, beige, and green. Our data set is now up to a little bit over 90 buildings, and normalized by meter squared of building. This is the master format categories, the material types of all of the buildings we've studied. So here on the left, we have accessory dwelling units, which is a type of building we're seeing becoming more and more popular in North America, where you have a house and it has a backyard, and in the backyard, you build a second, generally smaller house. It's a way of doubling the density without changing the texture of the neighborhood very much. Then we have here a big chunk of 40 single family homes, which is the dominant way of building in North America. And then we have what's called missing middle, which is what I showed on the new types of forms, which we're starting to make legal again in Toronto and in other places. Things like 3 apartments in one building, or a low-rise apartment building up to sort of 3 or 4 stories, stacked townhouses, those types of buildings. We're just getting into the data on those, which is why there's 5. We'll have by the end of the summer probably about 20 of this type. Then tall high-rise buildings, mixed-use buildings where there's usually commercial on the ground floor and apartments above, and then commercial and industrial buildings, which are not used for people but are used for workspaces. This is all of the data normalized per meter squared, and it looks like the low-rise buildings, the single-family homes, and the accessory dwelling units are doing quite a bit better than the high-rise buildings, which you tend to hear sometimes in the sustainability construction, that high-rise buildings have too much concrete, that they weigh too much. And also all of our buildings, even the ones essentially made out of wood, which is how we build above ground low-rise here, are dominated mass-wise by concrete. This brings us to a pretty nerdy question, but also a useful one about functional unit. This building in blue on the left and this one in beige on the right are both single family homes. They both have 3 bedrooms, but they're very different in terms of size, in terms of material use. And so we need to be a little bit careful when we categorize the functional unit. It's very common to say that functional units of buildings should be meter squared, that we normalize per meter squared, we write regulation like that, we measure things like that, but it can impact the interpretation of our findings pretty significantly. And when we looked in more detail for a paper we published last year on the material use in single family homes, we found that our conclusion about what is a sustainable building was heavily biased by the functional unit we used, by the way we normalized. So the top figure is the 40 buildings normalized per meter squared. They're organized from building 1, the smallest building on the left, to building 40, the biggest building on the right. And what we find when we normalize by per meter squared is that there's some variation, about 15%, but the buildings are pretty close to each other in terms of their material use and by extension, their embodied carbon across all 40 buildings. And in fact, building 1 is one of the worst buildings per meter squared, and building 40 is one of the best. Part of the reason we see this is because when we add more space to a building, we're often stretching the walls farther apart, and we don't have to add that much more materials relative to space to add more space. But when we normalize by just in one unit, so the entire building all at once, we see that there's way more materials and embodied carbon going into building 40, the biggest building, there is into building 1, which of course makes sense because it's a much, much bigger building. So even though it's adding materials at about the same rate as it's adding space, it's adding a lot more materials. And you might say, okay, well, maybe building 40 is a family of 12 people and building 1 is a family of 3 people. And so actually it's carrying way more people, and normalizing per unit isn't fair. So we also normalize per bedroom, which is a very good proxy of how many people live in a space. In North America, we generally assume that the primary bedroom has 2 people in it and that secondary bedrooms each have 1, though of course you could change that slightly. And when we normalize per bedroom, we see the same pattern as when we normalize per unit, which is that the smallest building is much more materially efficient, much more embodied carbon efficient in terms of providing bedroom space, which I think is a key function of a home, compared to a very big building. This is all a complicated way of saying something which should be pretty obvious. If we build really big buildings, we're wasting materials to house the same number of people, and that we're not adding much living function, though we could be adding fancy function or the appearance of well-being, or also the appearance of an experience of luxury. But if we're talking about having an equitable environmental society, we really need to ask ourselves, is that the kind of place we should be spending our limited resources? And when we normalize the entire data set by bedroom, we see huge differences in the appearance of how our data set looks. So this is how it looked before, and this is how it looks when normalized per bedroom. The institutional and commercial buildings have fallen off. And so what we have left with are just buildings that include a residential component. And so the single family homes, some of them, which have a lot of bedrooms per space, look quite a bit better than the ones that have very few bedrooms. Many of the single family homes now use more materials than the high-rise buildings and mixed-use buildings. The missing middle buildings look like a very efficient way of using resources. And our secondary suites, which are built in people's backyards, again, tend to do better than single family homes per bedroom, but with one exception. This one building here, which had a full basement and only 1 bedroom, is actually the most materially efficient building in our data set, very slightly beating in terms of bad efficiency this building here, which is a 3-bedroom, 4,000 square foot home built in the countryside. We also looked at the data divided between above ground and below ground. So what you see here in white is material use above ground, and what you see here in black is material use below ground. And so what we're seeing is there's a massive amount of materials going underground. And this is driven by two main things. One, underground parking, and two, the expansion of living space underground, which is becoming more and more common. We have strict rules about where people are allowed to build. So the envelope of your home, the occupancy of a home on its own land, what's called the floor area ratio, are heavily regulated. But if you build below ground, that doesn't count. Below ground space doesn't count to the zoning. And so we're starting to see in all new buildings, a full height basement, and even in some buildings, what's called an iceberg home, where you have more than one basement under the building. Exactly the same meter squared of living space built above ground would use much, much less materials, because anything built below ground has to also resist the soil loading and the water loading. It tends to be built out of concrete. It's much, much more materially inefficient. So these are all numbers from mostly Toronto, but others from North America, where we tend to build fairly similarly. So in other work, we've also looked, how does this compare to building around the world? And my PhD student, Aldrich Arcio, has looked at single family construction in Toronto compared to Perth and compared to Luzon in the Philippines. I think Luzon is probably the closest to construction styles in Israel, because most buildings are built out of reinforced concrete and then given cladding on top. And the construction of basements is quite rare. In Toronto, we build stick frame wood buildings with a lot of insulation with concrete foundations and basements. And in Perth, the standard construction is brick on a concrete slab with no basement. Almost all of the buildings had 3 bedrooms. Toronto ranged from 2 to 6, in Perth from 3 to 5, and in Luzon from 2 to 6. And when we look at the buildings compared to each other, again, according to the 3 functional units, the top normalized per meter squared, in the middle, just the materials in each individual unit, and the bottom normalized per bedroom, we see that the choice of how we normalize changes completely our interpretation of which construction type is the most sustainable. In Lausanne, where they're building both above and below ground and the foundation out of concrete, there is a huge amount of material use per meter squared. Concrete is a very heavy material. It's very greenhouse gas intensive. And so it's using a lot of resources. But with the exception of these 2 very, very big houses, most homes in Lausanne are relatively small. And so when we normalize per bedroom, and it's providing the same number of bedrooms as Toronto, or often more than Perth, we see much less material use overall per bedroom and much less material use overall, the middle figure, because the houses are just smaller. And so if we use the standard metric, Lausanne looks like the most unsustainable place. If we use per bedroom or in total, Toronto does. Again, highlighting how important it is, we think, not just about the per meters numbers, but the overall and per function material use. Okay, so I've talked a lot about buildings, but of course we know that's not the only place the materials go. Transportation infrastructure is a huge consumer of material use. In Austria, in a recent paper, it showed that construction material use was going about 50% into transport. The share of material use in transport changes dramatically with the urban form. We know that from existing research that in areas that are highly urban, so denser and taller, we see most of the material use going into buildings, 7 to 80% often. But in areas that are low density and more spread out, we see a lot more going into horizontal infrastructure, which includes transportation and water. From other people's work, it looks like for water infrastructure, if you go from a sort of meandering streetscape and low density to high density and a grid streetscape, you can decrease the embodied carbon in your water infrastructure to 1/10, so by 90%. So I'm going to share some research we've done on transportation in Toronto. We looked at, in Toronto, where all of the construction material use was in our roads. We looked at the granular level, the concrete, and the asphalt as well for the entire city. And we found a couple interesting things. One of which was that our material use in our roads is completely politically dominated more than anything else. So in 20 years ago, Toronto was combined into one city from what had previously been 5 different cities, which had their own design codes, their own approaches to construction. And you can see in the red line here, the formal municipal boundaries of what had been Toronto. And you can see in the shading here, the thickness of the granular levels around the city in 2018, which was about 20 years after the city had become one. And even 20 years later, you can see perfect outlines of the formal municipal boundaries, which shows that there's just a preference, right? All of them were engineering developed, all of them were engineering guides, but the soil is not changing, the loads are not changing that dramatically as we moved across these boundaries, which are very, very close to each other and are now within the same city. We officially now have one universal design guide across the entire city, but we found that the materials in the ground diverged from that in massive ways. We also then looked at how efficient we are in delivering materials in the ground infrastructure to how many jobs and people there are in different parts of the city. And the darker a place is showing up on this map, the more materials there are in the ground and the less jobs and people there are nearby. So this is really highlighting places where we've built a lot of infrastructure and we're not using it very intensively, and parts of the city that could do with quite a bit of more development and infill. What is happening in a bunch of these parts of the cities is that they were built out as single family homes, and they've been losing population over time as families get smaller and as people get older. But we have very strong zoning laws and often quite a bit of resistance into development. And so while the city itself is growing by about 80,000 people a year, these areas tend to be losing rather than gaining population. All right. So finally, to wrap up, I have a couple take-home points. One is we need to be taking the materials we use really seriously. Not just in thinking about how to recycle them, but how much we're using up front. It's a huge driver of climate emissions. It's a huge driver of cost. And it's now growing really, really quickly. We're using more in total and more per person. And it's happening while we're not paying that much attention. When I talk to other people about my work, they tend to say, oh, I've never really heard of this issue. But they have heard, for instance, of how bad for the environment it is to fly. Flying is 2% of global greenhouse gas emissions. Concrete and steel alone are probably about heading on 20%. And we're really just not talking about it enough. We need to both get better at making the materials, but also get better at using much less of them. Infill, so when we build things in the in-between spaces, are using less materials. And so they tend to be much better for the environment. But it's not because of anything magic necessarily about infill. It's that we're building them smaller. When we're building in denser places and doing density, we tend to build buildings smaller. That's the most efficient way to use less materials, make it less big. Also build less underground, which means that building less parking underground and building our living space more above ground than below ground. To this end, shared space, if we're making things smaller, it's a really important driver of making sure people have a good quality of life. In North America, we've seen housing size double over the past 50 years. And part of what has driven this is parking, but part of providing indoor parking for cars. But part of it is that what used to be public space, what used to be things we did together, we increasingly do alone. So people have big yards instead of going to the park. People have huge spaces for entertaining that they don't use that much of and don't share instead of using communal space. As we go through the famous public squalor and private wealth our houses are getting much bigger and our material efficiency is getting much, much worse. On the flip side, people who live in condos and apartments are often losing access to amenities. And so apartments are getting, at least in my area, are getting smaller. And people don't have public amenities to make that a nice way to live where you want to live for your entire life cycle. And so people live there for a while, but then eventually want to get out into a bigger home because they don't have access to the services they want to make it a viable life for them. Form has a huge impact overall on material use. And this is something that is, yes, driven by policy, but largely in the control of the engineer and the architect. We can design spaces that are smaller and nicer. And so that is the final challenge that I will leave with everyone who works in the space. We need to design spaces that are both good socially and environmentally. And the third way through between our challenges of having a huge infrastructure deficit, which requires resource use, and having a cap on how much we can tolerate in terms of planet carrying capacity for resource use. So we have to have good, desirable small spaces. All of the images that I am showing at the bottom are from a website or a YouTube channel called Never Too Small, where they do little documentaries on beautiful small spaces. And yes, many of them are for one or two people, but they also show them for families. And at least here, most people live alone or with one other person for most of their lives. And so we can talk about changing that, but we can also think about right-sizing our infrastructure. So I just want to say thank you to a large number of people and bodies that made this possible. There's a huge team of students who have been involved in the work, especially the material takeoff work, which, as I mentioned, takes a huge amount of time. A very large number of data partners who have shared information with me. This would not be possible without private companies sharing their data. And because it's so time consuming and takes so many people, funding has been absolutely critical to keeping the research going. So my thanks and acknowledgement of all of these people. And it looks like I spoke a little short, which almost never happens to me. So hopefully we'll have lots of questions and we can do that for the next little bit. So thank you for listening. I will stop sharing my screen.
Thank you so much. This was a really amazing talk. I would actually like to start with a question, and then I will move and give the audience here in the room and also on Zoom to ask. I would ask for your advice on how are you engaging? You know, you were sitting in academia, young, energetic researcher. How do you engage with industry, with government, with local government and national government to actually pursue this, to share information, to help move from theory to practice? You know, this is part of what we try to discuss today. We are talking a lot about sustainability and circular economy, but okay, theory, enough with theory. We need good research, good data, but we also want to make sure that the other players are moving into practice. So any thoughts about that? How are you doing it there?
Yeah, so there's a bunch of different ways that I'm working on it. And of course, there's always more to do. So one of the things that's been very effective for me in getting my research out of, you know, my office and out of my head and into the world has been talking to the press about it. So the non-academic press. So I've gotten to know some of the reporters in the city space and the building space or the architecture space. And if I think I have work they'll be interested in, I send it to them. And sometimes they write about it, or also they know me. And so if they're writing about the topic, sometimes they'll call me. Also, the University of Toronto has an internal press office, and they'll write articles and put them in U of T News, and that gets read by a surprising number of people. And anytime I've had work in our internal news service, it eventually gets picked up by our external news services, and I then usually hear about it from somebody in private sector or government. So making the information as publicly available and as digestible to a mainstream news audience as possible has been very effective for me in communicating the work beyond the academic publications. Also, I just reach out to people directly. So, you know, I've been back in Toronto now for 6 or 7 years. I've gotten to know people. You know, it was easier before COVID because we'd run into each other at events and I could introduce myself, or they would see me present. But also I reach out to them. I offer to talk to them about my work, or often to talk to their group about my work. I invite them to partner on the research. The research I just showed has more than 40 private sector partners, and that has just been gathered by asking them over time. If I find out about somebody who builds a building, I email them or reach out to them or ask for an introduction. I ask everybody I work with to introduce me to other people, and then I study their buildings and I give them a presentation quite similar to the one I just gave you, but with a focus on their own buildings, which we can pick up and de-anonymize when I'm talking to the people who built them or designed them. And I do that as much as I possibly can. Yeah, those are the main ways.
And do you feel industry is actually moving in implementing the choices, the better choices, you know, taking into account, you know, these long-term calculations and impacts now when they make business decisions?
They're trying. They're very interested. So whereas when I started talking about embodied carbon 12, 15 years ago, at the beginning of my PhD, nobody cared. You know, I was in the private sector before, and part of the reason I needed to leave was because people didn't think these were interesting questions. That has changed almost completely in the last 3 to 4 years in Canada and in North America to a larger extent. It's changed faster in Europe, where, you know, you're now seeing the UK, a conservative government passing laws to mandate embodied carbon is reduced in construction. So they're quite a bit ahead of us. So the writing is on the wall. People are seeing that it's coming. So and it's starting to show up in regulation. So whereas 10 years ago, people knew they needed to talk about operational energy and started hiring building scientists, and that became a standard part of design that you'd make an energy model and test it. That is just starting to happen with embodied carbon. People know the regulation is coming. They know they need to care. They're trying to figure out what to do about it. And so often they're quite excited to talk to someone who's thought about it for a long time and give them some numbers. That doesn't mean they listen to me, but in terms of practice right away, but it does mean they're more interested to talk, certainly dramatically more than they were 12 years ago. And like I said, it's showing up in regulation. So even people who aren't necessarily interested are starting to get interested. Toronto has a green standard, which they tighten every sort of 4 to 5 years. And the new version includes embodied carbon measures for the first time.
Thank you. Anyone has a question in the crowd here or in the Zoom? Shoshana? Yeah, I saw one comment in the Zoom, but before that, anyone here in the room? Ready to eat, huh? Okay. David, do you want to, you still here? So, yeah, you're in.
Yes.
Hi, David.
Hi. Yes, thanks to all the organizers, and thank you, Shoshana. I found that really fascinating. I'm David Perlmutter from Ben Gurion University, and what I'm wondering is whether the two parts of your research could be combined, that is taking the building-related materials and the transport infrastructure materials, be normalized and combined so that we could be able to evaluate urban design at a neighborhood level or a district level more comprehensively to make better decisions about urban form?
So the short answer is yes, and we're working towards that. And we could probably already do a proxy now. There are places in the world where people have done bottom-up city scale material flow analysis. I think one of the most complete was done in China, I think for Beijing, where they did include transportation and other infrastructure as well as buildings. Most bottom-up MFAs only do buildings. We have not done it in the standard way for a couple mostly academic reasons, which is that the standard way to do it is to assign a typology. So you say we have 15 or 20 different types of buildings in our city, and there are 100,000 of this kind and 100,000 of that kind and 20,000 of this kind, and multiply them across and then make maps. The part of the work that we're doing, which I didn't talk about too much today, is how accurate those typologies are. And we have found in our own published work that they're very inaccurate. We've tested the typologies against measured data for transportation in that same paper. We found that in many cases it would be quite wrong. And we've also tested just what's the general variation within a type, and found that even within buildings of the same year of the same type, we're seeing 50 to 20% variation just in the typology. So that's the reason we haven't done that, is because it would be off at a range of scale that I think might matter. So if the numbers are off by, let's say, 20 to 30%, which I think would be a very accurate bottom-up MFA, that might be within the scale of change that we could observe by material change or form change. So we're working on ways to increase accuracy in data. That was one of the motivations for starting to do a bottom-up material takeoff for so many different types of buildings. I will admit, as with most research projects that end up consuming your time, I was naive about how long it would take and how much effort would be included, which is probably a good thing, because if I'd known, I might not have started. And now I'm very thrilled by the work, but we're working on it. It's just going to take us a little bit more time. If we needed policy level advice, we could absolutely do it quickly, and we should. But for an academic process, we're working on improving accuracy and methods to eventually what I hope will be a quite easy method that's very accurate if we do this well. We're just not quite there yet.
Thanks a lot. I'll look forward to see how you progress with it.
Thanks.
We did a very initial study in Beersheba here in Israel, but taking actual case study neighborhoods. So they were different typologies, but they were actual examples of different typologies, and there were substantial differences, as you can imagine.
Great. I would love to see that. Please send it to me.
Certainly.
Great. Shoshana, thank you so much. We will release you to your morning. And thank you so much again for your participation and for bringing us this knowledge. And I hope to see you soon. Are you coming to the DRC?
I hope so too. Thank you for having me.
Thank you. Okay, so it's time to conclude our conference. I want to start by saying we are concluding, but as much as we think about it, this is only the beginning, for new collaborations, for more discussion among the different organizations that participate here. I think I can speak in the name of all of us here that we really invite collaborations and working with real data and creating some powerful impact here in Israel. I think it's time to make an impact first here in Israel. I would like to thank all of my partners and colleagues, and especially really Adi for putting all of this event together from first to end. I would also like to thank the Technion for supporting and feeding you all, and for the Porter School for taking care of everything else and hosting you here today, and the general support of having such events, which are, not necessarily poor academic conferences, which I personally believe in a lot. I think we must combine, we must talk with each other, we must share knowledge, and that's the only way to really do something that is powerful. I hope you enjoy your light lunch, and we look forward for being in touch. Shani, Sabrina, do you want to say anything? Thank you.